In the quietude of his backyard observatory, an amateur astronomer made a discovery that fundamentally defied conventional astronomical expectations. 5 distinct points of light, arranged with impossible precision, formed a perfect circular halo around an object originating from beyond our solar system. Though Ray possessed neither an expensive telescope nor professional image processing capabilities, his footage captured a geometric configuration so strikingly symmetrical, so eerily coordinated, that even seasoned scientists find it difficult to dismiss as mere instrumental artifact, dust particles, or diffraction patterns. Some optics experts label it a technical anomaly. Others, more speculatively, whisper of escorts accompanying the visitor. Adding to the intrigue, the space agency, typically swift in releasing observational data, has maintained an unusually profound silence. Remain with us. Tonight we embark on a meticulous examination of every captured frame, every detected anomaly, every detail that renders this the most perplexing interstellar traveler humanity has ever encountered. Because something undeniably moved within the coma surrounding that comet, and we must identify its nature before it disappears entirely. If this mystery resonates with you, if an insatiable pull draws you toward the unknown, join this journey for future revelations. Share your location and the local time in the comments below, and offer your thoughts on this startling development. We are grateful for your presence and participation in this collective exploration. What Ray actually captured is nothing short of breathtaking. Picture this, scrolling through digital images late into the night, perhaps. Then a sudden halt. 5 points of light, perfectly spaced and uniformly luminous, glow with unnatural symmetry, encircling an anomaly, something entirely out of place. The image itself may be faint yet remarkably clear, perhaps over-enhanced, yet the pattern possesses an undeniable arresting quality. A viewer in the digital commentary section writes, "This isn't natural." Another responds, their words echoing the growing curiosity, "We are not alone." A third, albeit more reserved, presence lingers just beyond the threshold of detection, drawing the eye irresistibly despite its subtlety. Perhaps it's rooted in a primal instinct, a deep-seated cognitive bias that associates symmetry with intelligence and patterns with intention. The meticulously arranged formations circling an enigmatic object, originating from outside the solar system, appear too flawless to be dismissed lightly. This is the footage captured by Ray, an avid amateur astronomer, equipped with a respectable array of tools and a fervor for uncovering celestial mysteries. His gaze was directed towards 3IATLAS, the newest interstellar traveler to grace our cosmic vicinity.
The visual evidence he amassed has sparked widespread debate online, bewildered experts in optics, and engendered a conundrum that remains unaddressed by NASA. Thus, we shall unravel the intricacies of Ray's recording, ponder over its implications, and examine why even the most skeptical minds are struggling to provide a straightforward explanation. Ray operates with equipment that would be familiar to any dedicated amateur astrophotographer, with no advanced instruments like the Hubble telescope at his disposal. His observatory is more likely to be found in the garage of an enthusiast, featuring an 8 to 14-inch Schmidt-Cassegrain telescope and a conventional RGB sensor, devoid of any infrared or ultraviolet filters. This configuration is standard among enthusiasts, with thousands possessing similar setups. On a clear night, he aimed his telescope at 3IATLAS, captured several images, and embarked on the meticulous task of stacking these frames to diminish noise and enhance faint features. This process is routine for amateurs globally night after night. However, this instance proved exceptional, as an anomaly emerged that was not part of the plan. During astronomical observations, faint background stars reveal slight streaks due to minor tracking inaccuracies. Such artifacts are commonplace. However, upon initiating careful stacking and sharpening of the captured frames, astronomer Ray discerned 5 distinct bright points emanating from the image noise. These points arranged themselves in a loose circular pattern encircling the comet's central core. Their placement was neither random nor scattered. It was deliberate and persisted across numerous separate captures, observations taken minutes apart. If these luminous spots were merely defective pixels or sensor-generated noise, their appearance would be haphazard, flickering inconsistently from frame to frame. The contrary reality was evident. The points remained consistent and maintained their configuration. This consistency naturally prompts inquiry into the possible origins of such bright spots surrounding a celestial body. Diffraction represents the most immediate suspect. The bending of light around the edges of a telescope's optical components can indeed generate rings, spikes, or distinct patterns. Every astronomer familiar with the field recognizes this phenomenon. Pointing a telescope at a bright star typically produces a characteristic diffraction pattern determined by the specific telescope design. Yet, this explanation encounters a significant obstacle regarding the observations. Diffraction patterns are intrinsically dependent on the angle of incoming light. They shift and change shape dynamically as the telescope tracks moving objects or as the object itself shifts relative to the optical axis. The 5 points observed within Ray's images defy this expected behavior.
They persisted steadfastly, remaining roughly equidistant from one another throughout the sequence. Furthermore, while diffraction can form rings, it does not commonly manifest as 5 separate, intensely bright nodes spaced evenly around a dynamic, outgassing object like a comet. The next potential explanation considered is simple background stars. Could minor tracking inaccuracies have smeared stars into elongated arcs that merely coincidentally aligned around the comet's position? This hypothesis, however, collapses under scrutiny of the timescale involved. The exposure durations employed were sufficiently short to ensure that stars appeared strictly as points or only very slight streaks, rendering the formation of distinct arcs around the comet implausible. Stars remain fixed, showing no sign of orbital motion, their paths appearing as straight drifts within the frame. These points, however, defy stellar behavior. Observing their movement reveals the intrigue lies here. Ray's capture wasn't a single instant, it encompassed several sequences spanning approximately 30 to 40 minutes. Within these sequential images, the 5 points demonstrably altered their position. Not with dramatic shifts suggestive of orbiting bodies, but subtly changing their configuration relative to one another and the comet's nucleus. Frame 20 presents one distinct arrangement. Frame 14 shows a slight rotational shift. Frame 9 depicts an again altered configuration. Witnessing this progression in real time would create the undeniable impression of something in motion, something circling. This perceived movement is precisely what sparks such unease. Stacking images, the technique applied, can indeed generate deceptive effects. By layering multiple exposures, random noise tends to average out, while persistent features gain reinforcement. Any genuine structure within the comet's coma, perhaps jets emanating in specific directions, becomes strikingly apparent under stacking. Conversely, stacking possesses the power to magnify unwanted artifacts. A single defective pixel appearing consistently across frames manifests as an unnaturally bright point in the composite. A faint background galaxy coincidentally aligned with the comet's trajectory can manifest as a phantom companion. Ray's stacking process introduced valuable consistency for signal enhancement, yet simultaneously created the potential illusion of coherent structure amidst underlying chaos. Optical scientists hold divergent views. Some examine the final images and perceive exactly the expected outcome resulting from the interplay of dust jets combined with imperfect data processing techniques. Comets naturally expel material in an inconsistent manner. When a comet's nucleus rotates and possesses active vents, it can generate conspicuous clumps of dust within its coma. These dust aggregates effectively scatter sunlight, becoming highly visible.
From specific viewing perspectives, particularly those lined favorably, these concentrated dust clumps may seem to encircle the central nucleus, However, applying sharpening algorithms to observational data can artificially accentuate these features, exaggerating their edges and giving the entire formation an unnervingly geometric appearance. Scientists have dubbed this artificial-looking cluster an artifact cluster, suggesting it holds no intrinsic significance. Yet not all researchers are convinced by this explanation. The precise spatial arrangement of these features troubles some observers. Even when generously accounting for potential projection effects and the complex dynamics of dust movement, achieving 5 bright nodes positioned roughly equidistantly around the nucleus appears statistically improbable. While not categorically impossible, the configuration is undeniably strange. This initial puzzlement is compounded by the observed minute scale evolution of the phenomenon. Here lies the fundamental issue. If these features are merely transient dust clumps residing within the coma, they should disperse relatively quickly. The coma itself is an expanding cloud of gas and dust. Material within the coma does not maintain stable orbits. Instead, it flows outwards, propelled by solar radiation pressure and the comet's own vigorous outgassing. Consequently, any discrete features within the coma ought to drift apart, spread thinly, and dissipate into the surrounding background haze. What defies this expectation is the persistent coherence of the 5 points over tens of minutes. They exhibit movement and positional shifts, but crucially, they do not dissolve or blur into insignificance. Their enduring structure implies the presence of some underlying organized framework, something potentially anchoring those illuminated regions. Speculation arises regarding the geometry of the vent jets themselves, constantly replenishing material at specific locations, or perhaps a complex interplay of perspective effects. Yet the persistent anomaly fuels a more profound suggestion. It might hint at something fundamentally different. Predictably, the public response ignited widespread attention. Online communities erupted in discussion. Conspiracy theorists seized upon the unusual configuration. The phrase, "too perfect to be random," rapidly proliferated across comment sections, reflecting the public's fascination and unease with the seemingly deliberate arrangement. The enigmatic object now known as 3IATLAS has ignited diverse speculation. Observers coined the term escorts for its peculiar companion features, while others proposed the existence of probes. More dramatically, some scientists questioned whether 3IATLAS is truly a comet at all, suggesting instead it might masquerade as one. This growing swirl of conjecture, however, masks a fundamental scientific inquiry.
Even meticulous researchers are grappling with a core question: what natural mechanism could produce this distinct configuration? And why does the pattern bear such an uncanny resemblance to structures designed to maintain a perimeter? This exploration will delve into several perplexing aspects. We will examine peculiar rotational patterns that defy conventional understanding, the geometry of its jets, which contravene established comet physics, demand scrutiny. Furthermore, subtle anomalies within the raw data, overlooked even by its initial analyst, require attention. Finally, we must confront the unasked question lingering within the scientific community. If 3IATLAS is merely a comet, why does it appear accompanied? Part 2. The rotation. Comet rotation is a common phenomenon. These irregular aggregates of frozen volatiles and silicate matter typically tumble through the void. Solar heating induces asymmetric vaporization of surface ices, generating directional jets that impart or alter rotational velocity. Most comets exhibit slow spin rates, measured in durations ranging from several hours to multiple days. Astrophysicists track these bodies over extended periods, meticulously observing minute fluctuations in brightness and the evolving structure of their diffuse atmospheres. This patient, methodical analysis gradually reveals orientation and rotational speed. It is precisely this established protocol that renders the observations made by Rye during observations spanning under 2 hours so profoundly anomalous. The comet designated 3IATLAS appears to be exhibiting an extraordinary and rapid spin. The manner in which it rotates seems to deviate significantly from established patterns. This peculiarity was first observed by an astrophotographer named Rye while analyzing his series of captured images. Within the comet's coma, the hazy envelope of dust and gas surrounding its core, Rye detected an unusual dynamism. Far from being a static feature, the density within this cloud visibly shifted over surprisingly short intervals. Features that appeared bright moments before would gradually dim, while other regions would intensify in luminosity. This progression suggested the comet was actively rotating, continually presenting different aspects to his telescope. The phenomenon bears a resemblance to observing the sweeping beam of a lighthouse. Although the structure itself remains stationary, the rotating beam creates the impression of change in what is seen. In this cosmic instance, however, the source of the apparent change is the comet itself, acting as the rotating body. The beams observed are instead streams of material, jets erupting from its surface. This observation, however, introduces a layer of complexity arising from the imaging equipment used.
Standard astrophotography setups, particularly those incorporating accessories like diagonals or specific corrector lenses, can inadvertently flip the captured image horizontally. Consequently, Ray's initial analysis showed rotational motion appearing clockwise in some images and counterclockwise in others. This variation depended entirely on the orientation of the image as processed, which is a known and expected artifact of the equipment. To discern the comet's true motion, a correction for this mirroring effect was necessary. When the images were properly oriented and the actual movement of features within the coma was meticulously tracked, a distinct pattern emerged. The data confirmed the comet is indeed rotating. More remarkably, the rotation period indicated by this corrected analysis appears astonishingly brief, potentially on the order of mere minutes. This finding is particularly noteworthy because such a rapid spin rate is highly atypical for a comet nucleus possessing a diameter measured in several kilometers.
It might also clarify why these shifts appear too consistent to be random fluctuations. Precession possesses inherent structure and periodicity, which can manifest with an apparent regularity that seems deliberate, though it is purely physical. As material jets violently eject from a comet's surface, it imparts momentum. Should these jets exhibit significant activity on one hemisphere while remaining minimal on the opposite side, a rotational force, or torque, is generated. This torque can alter the nucleus's spin, either initiating rotation or modifying its existing rate. Astronomers recognize this process as a legitimate physical phenomenon. Space missions, such as the European Space Agency's Rosetta probe, have directly witnessed this effect. Observations of comet 67P Churyumov-Gerasimenko revealed the nucleus undergoing a measurable, gradual change in its spin state over the course of many months. However, the interstellar object designated 3I/Atlas appears to be undergoing a drastically different and far more rapid rotational shift. Observations suggest this change occurs over minutes, not months. This stark discrepancy implies either exceptionally intense outgassing activity or the presence of another, unidentified force influencing its motion. Alternatively, the observed rapid rotation could simply be an observational artifact. Imperfect tracking of a celestial object during long-exposure astrophotography can create the deceptive appearance of rotation in an actually stationary body.
If the telescope's tracking were not precisely compensating for the comet's motion across the sky, the comet's diffuse coma would drift subtly within the camera's field of view. Distinctive features within this coma would consequently shift position frame by frame. When such drifting images are subsequently stacked together, this motion can be misinterpreted as genuine rotational movement where none exists. This well-known technical issue is termed field rotation, a common challenge encountered in astrophotography. Crucially, the tracking data associated with observations of 3I/ATLAS does not exhibit this field rotation effect. The background star field remains sharply defined and its positions demonstrably stable across the images. If field rotation were the cause of the apparent rotation, the background stars would exhibit the same drift and positional shifts. They do not. This absence of field rotation in the star field is a significant point of observation. It is at this juncture that some observers began speculating, because if 3I/ATLAS is indeed rotating rapidly, and if that rotation demonstrates a remarkable degree of stability rather than chaotic tumbling, the motion begins to evoke a specific artificial resemblance. The pattern echoes that of engineered objects, such as spacecraft or satellites, which are meticulously designed to maintain precise orientation.
In aerospace engineering, this controlled adjustment of an object's attitude is a fundamental principle. Achieving precise orientation for a spacecraft necessitates either rotational stabilization or the application of thruster firings. The observed rotational axis appears unnervingly steady, exhibiting a quality reminiscent of maintained control. While it is imperative to state unequivocally that no evidence suggests artificial construction exists, the pattern's distinct regularity inevitably prompts comparison with engineered systems. Once this possibility enters discourse, it proves remarkably persistent. Genuine physical principles, however, offer plausible explanations for phenomena such as apparent spin reversals and rotational illusions. One such principle is frame aliasing, also known as the wagon wheel effect. This optical illusion occurs when observing a rotating object at intervals not perfectly synchronized with its rotation period. As witnessed in cinematic depictions, a wheel spinning forward may visually appear to reverse direction due to the camera's frame rate failing to match the spinning speed. Astronomical observations are susceptible to this same phenomenon. If exposure intervals during imaging were spaced either correctly or incorrectly with respect to the rotation period, the resulting motion could convincingly appear to reverse or stutter. This constitutes a perceptual illusion, yet a remarkably convincing one. The relationship between this rotational observation and the 5-point anomaly further fuels inquiry. If both characteristics are genuine, a potential linkage exists. Imagine a central nucleus possessing 5 active emission points uniformly distributed around its equatorial plane. As the nucleus rotates, each vent activates sequentially, ejecting jets of dust that manifest as discrete bright pulses. From a distant vantage point, these individual jets would not be discernible. Instead, one would perceive fixed points of luminosity, maintaining their position relative to the nucleus, appearing to move in concert as the body turns. This natural mechanism provides a coherent explanation for the observed pattern. The observed rotational dynamics align with physical laws, yet achieving this precise vent configuration demands an almost implausibly ordered structure. This brings us directly back to the core enigma. Why such remarkable symmetry? Why does the object appear meticulously engineered? As of yet, NASA has offered no official commentary regarding its rotational parameters. Crucially absent remain any declared spin period, alongside analyses of potential precession or wobble. This collective silence is profoundly conspicuous. Historically, the detection of an interstellar visitor prompts immediate data dissemination from major agencies.
Standard preliminary reports typically include orbital elements, photometric brightness variations, and rough dimensional estimates.
However, the expected rapid transmission of information regarding 3I-ATLAS has noticeably decelerated. Possible explanations abound. Perhaps scientists await additional observational data. Perhaps they are rigorously validating and revalidating their predictive models. Or perhaps they are confronting the very same peculiarities captured by astronomer Ray and grappling with how to offer a coherent explanation that avoids reigniting the intense media scrutiny witnessed during the Oumuamua incident. That episode saw theories rapidly escalate into increasingly exotic interpretations, a scenario most astronomers are eager to avoid repeating. Consequently, we are left with a comet exhibiting an implausibly rapid spin rate, rotating with unnerving smoothness. Furthermore, its surface features shift in patterns that are both systematically regular and fundamentally bizarre. We are left questioning the presence or absence of significant torque and wobble, and speculating on any potential connection to those 5 distinct luminous points. Ultimately, we are left wondering whether the rotational behavior serves as a genuine clue, a vital key to unraveling the object's anomaly, or merely represents another perplexing layer obscuring an already profoundly baffling discovery. Next, we will examine the jets themselves, their geometry, which appears to defy established physical principles, and explore the concept of shadowing, specifically focusing on why the observed symmetry remains such an unresolved puzzle. This analysis forms Part 3, Jet Geometry, Shadowing, and the Enduring Enigma of Symmetry. Comets are inherently disordered, a fundamental lesson encountered early in their study. Far removed from idealized, smooth spheres governed by orderly processes, these celestial bodies are profoundly jagged and irregular. Their surfaces are pockmarked with pits and fractured terrain, coated in layers of dusty lag deposits. Beneath this crust lie pockets brimming with volatile ices, heating unevenly as the comet nears the sun. When these frozen materials vaporize, their release is not uniform. Instead, they blast violently from localized vents, creating asymmetric jets. These jets twist and spiral chaotically as the comet's nucleus rotates. The consequence is a state of beautiful, dynamic chaos. No 2 comets appear identical, and even a single comet undergoes dramatic visual transformations from one week to the next. Therefore, encountering a comet displaying repeating symmetric structures within its coma immediately warrants skepticism. Nature, especially in the realm of cometary behavior, rarely produces such precise symmetry. Not under these circumstances, not typically.
It displayed non-gravitational acceleration, implying some form of material ejection, yet astronomers never detected a visible coma or distinct jets. Its motion suggested an unseen force acting upon it, leaving no obvious physical trace. Conversely, the second interstellar traveler, Borisov, displayed the opposite characteristics. It possessed strong activity, featuring a bright, expansive coma and clear evidence of carbon monoxide outgassing. Its jets shifted and flickered as it tumbled through the inner solar system. This chaotic, asymmetric behavior aligned perfectly with expectations for a comet. Neither of these interstellar bodies presented anything resembling the symmetric structure captured by the ATLAS telescope. Neither observation featured a distinct ring formation of bright nodes. Furthermore, the arrangement lacked any apparent coordination between the points. However, the imagery captured by Ray presents an alternative perspective. The 5 luminous points are not isolated phenomena. They demonstrably correspond to specific structures within the comet's coma. By increasing contrast sensitivity and carefully following the faint strands of ejected dust, one can discern radial patterns emanating from the central nucleus. These intricate patterns intersect precisely at the locations of the bright nodes. This configuration strongly suggests the presence of multiple jets erupting simultaneously from the nucleus. Each jet appears to generate a localized bright region formed where dust effectively scatters sunlight. Yet, a significant scientific challenge emerges. The coordinated activation of 5 jets positioned at regular intervals around the nucleus contradicts natural expectations. Cometary geology, fundamentally shaped by accretion, ancient collisions, and millennia of uneven solar heating, inherently produces irregular vent distributions. Discovering 5 active regions spaced precisely 72 degrees apart represents a statistically improbable scenario. While not categorically impossible, such a configuration warrants serious consideration. Fortunately, viable scientific explanations do exist. One plausible mechanism involves dust vents aligned near the comet's rotational axis. If the orientation of the comet's spin axis happens to be favorably positioned relative to the Sun, and if vents cluster near the equatorial region, their activation could occur sequentially as the nucleus rotates. From our fixed vantage point, this sequential firing would create the compelling illusion of all 5 jets igniting simultaneously. This phenomenon constitutes a geometric projection effect. The visual impression parallels that of a rotating lighthouse beam appearing steady when observed from a specific stationary position. This rotational explanation holds mathematical validity. The described vent alignment and distribution fit physical principles, yet demand an exceptionally precise configuration.
The accumulated coincidences make this scenario improbable. An alternative explanation proposes resonant structural characteristics. Consider a nucleus possessing internal fractures or layered formations sculpted by immense thermal stress over billions of years. As it approaches the Sun and heats, these existing cracks might channel escaping gas along predictable trajectories, generating repeating patterns. Certain asteroids exhibit comparable behavior, locking into resonant spin states where surface features manifest with striking symmetry. Should 3-1-ATLAS possess an internal structure conducive to such resonance, its jets could appear deceptively organized without implying artificial origin. Instead, they would simply follow natural conduits etched by geological processes, resulting in patterns that fortuitously resemble order. This possibility exists, though it too necessitates highly specific circumstances. Another factor involves variations in particle dimensions. The coma dust within a comet is not uniformly sized. It comprises both larger grains and microscopic particles. Each size interacts with light differently. Larger grains tend to forward scatter light more effectively, while smaller grains preferentially backscatter it. If the comet ejects dust possessing a particular size distribution exclusively in certain directions, it could produce bright focal points that appear artificially arranged. In reality, these would merely be manifestations of wavelength-dependent scattering effects intensified by the specific viewing angle. This phenomenon is well documented. It has been observed in other comets, typically producing subtle gradients rather than distinct sharp points. The intensity and clarity observed in rays capture significantly exceed this usual subtlety. Let us now examine the implications of shadowing. Observations reveal the presence of distinct, dark, linear features within the comet's diffuse coma. These are not merely faint regions, but noticeably dark areas, seemingly caused by an obstruction blocking illumination. Such shadows inherently imply underlying structural complexity. They suggest the existence of tangible forms capable of casting distinct silhouettes. Within the typical gaseous and dusty envelope of a comet, sharp shadows are unexpected,
as light is generally scattered and emitted diffusely throughout the cloud. However, if the comet possesses a more rigid core structure, perhaps one fractured into large identifiable segments, these segments could potentially project shadowed zones as they rotate. The Rosetta mission's study of Comet 67th P yielded an analogous phenomenon. Its characteristic rubber duck morphology generated shadows that fell across its own surface, producing striking light and dark contrasts. The 3-1 comet could exhibit similar behavior.
An unconventional morphology, rotating and casting shadows through its own expanding coma, could plausibly account for the observed dark ridges. Furthermore, this mechanism would logically explain the observed shifting of these ridges between sequential images. As the nucleus turns, so too do the projected shadows, causing the pattern to change. This explanation appears straightforward, yet the shadow's behavior proves not entirely consistent. While they do shift, correlating with the nucleus's rotation, they also exhibit a puzzling linkage to the bright features. Areas of intense brightness often appear near corresponding dark ridges, suggesting a potential connection between the two. This specific correlation presents a significant challenge for the simple shadowing hypothesis. It hints at the possibility of some organized structure within the coma itself. Perhaps dust lanes exist, regions where material aggregates more densely, thereby creating both bright, reflective points and adjacent dark gaps. Alternatively, the observed dark ridges and their association with bright nodes might be an artifact of the image processing technique. Excessive sharpening applied to enhance faint details can artificially generate dark halos encircling bright objects, effectively mimicking the appearance of non-existent shadows. Given that Reedy's processing pipeline incorporated aggressive sharpening to reveal subtle features, this digital artifact remains a plausible source for the phenomenon. However, this raises a further question. Why do these shadowed features also manifest within the less processed image frames? The phenomenon arises directly from the fundamental mechanics of image stacking. When multiple exposures of an object displaying rotational movement are precisely overlaid, repeating patterns naturally amplify through constructive interference. Concurrently, random noise inherent in individual frames tends to cancel out. Consequently, any consistent structural elements become increasingly pronounced and appear brighter in the composite result. This principle becomes particularly significant when observing celestial bodies like comets. If the comet's jet activity possesses even a subtle radial symmetry, the stacking process will inherently exaggerate and emphasize this inherent geometric quality. Effectively, stacking acts as a computational filter, inherently favoring structured order over chaotic randomness within the data. This inherent human tendency to perceive patterns becomes crucial to understanding the final outcome. Our visual cognition is remarkably predisposed to detect familiar shapes and symmetries, even where they may not objectively exist. We instinctively recognize faces within cloud formations, trace constellations across seemingly random stellar distributions, and often attribute deliberate design to ambiguous visual noise.
Therefore, the enhanced symmetrical patterns revealed by Ray's stacked images may primarily reflect our own deeply ingrained cognitive biases, revealing more about human perception than the comet's actual physical structure. Nevertheless, alternative explanations rooted in the comet's potential physical configuration must be considered. Certain asteroids exhibit distinctly faceted geometric shapes resulting from ancient collisional processes. If the comet nucleus, designated 3/ATLAS, possesses a similarly polyhedral structure comprising flat faces and sharp edges due to fracturing, its rotation would cause these differing planar surfaces to sequentially face the Sun. Each unique face would absorb solar radiation differently, potentially activating distinct vent systems at specific rotational phases. The sequential activation of vents would generate jet activity in a repeating sequence, yet maintain an overall symmetric geometric arrangement. A different yet analogous mechanism could be produced by a tumbling, cylindrical-shaped nucleus. As this elongated body rotates irregularly, identical structural features repeatedly present themselves towards the Sun and observer over successive rotations, generating a periodic pattern within the observed coma. Furthermore, the possibility exists that the observed object constitutes a binary system, two distinct bodies gravitationally bound and orbiting a shared center point. Each component of such a pair could independently contribute material to the surrounding coma, potentially creating complex, symmetrical patterns that visually coalesce into the appearance of a single structured object accompanied by apparent companions. Such an explanation would illuminate many aspects. However, no evidence confirms a binary system. Crucially, there are no periodic brightness variations, which mutual eclipses would inevitably produce. Furthermore, the star's trajectory shows no gravitational wobble. These missing indicators leave only speculation to fill the void. The most persistent, unsettling hypothesis then emerges. Could the object's shape be artificial? Might those 5 distinct jets function as engineered nozzles? Could its rotation be actively controlled? This notion seems utterly far-fetched at first glance, especially when considering our own achievements. Probes like Voyager, Pioneer, and New Horizons have already journeyed beyond our solar system. These machines maintain precise orientation using thrusters and spin stabilization. If humanity mastered such techniques, why deem it impossible for another intelligence to have done the same? Yet this remains pure conjecture. There is currently no tangible evidence supporting an artificial origin. The geometry, however, stubbornly invites the question, why does the object exhibit such extraordinary symmetry? Why does its configuration bear such a striking resemblance to a deliberate design?
And when attempting natural explanations, why do they invariably require increasingly improbable special conditions, perfect alignments, and sheer coincidence? The answer may lie hidden within the data itself, specifically in the intricate metadata accompanying Ray's observations. Details he overlooked, subtle anomalies within the surrounding star field, unexpected color shifts in the coma, micro-movements that defy the behavior of a conventional comet hold potential clues. We must examine these buried signals, filtering through layers of data processing and ingrained assumptions. Because if something truly anomalous is occurring with Oumuamua, the solution might not reside in what we readily perceive. It could lie in what we almost overlooked, the hidden metadata, the critical detail Ray omitted. Yet it is revealed through the images themselves. Every astronomical photograph carries latent secrets, a truth well understood by professional astronomers. The captivating image before you, a radiant nebula, a distant galaxy, or perhaps the faint trail of a comet, may seem to be the full extent of its revelation. Yet beneath this celestial showcase there lies a hidden layer woven into the very fabric of the digital file. This concealed information encompasses exposure durations, sensor thermal states, timestamps, tracking coordinates, and deeper still within the subtle nuances of pixel values and the interplay between successive frames. These elements hold the potential to disclose whether the object of our gaze is genuine or an artifact, natural or the manifestation of the impossible. Ray's photographs of 3 Lameas are no different. On initial inspection, they present 5 luminous points and an enigmatic rotation. Yet within the metadata, in the details Ray either overlooked or perhaps remained unaware of, there exist subtle indications of something more extraordinary. They do not constitute definitive proof, not yet, but these hints can be more unsettling than solid answers.
begin with the star streaks visible in his images. In the practice of astrophotography, the telescope must compensate for the Earth's rotation to keep the celestial object centered. A flawless tracking mechanism yields pinpoint stars. However, any imperfection results in smears, stretching stars into lines. This is a common challenge for every enthusiast and is considered routine. Ray's images indeed display these star streaks as anticipated, yet upon closer scrutiny, some of these streaks are curved, not dramatically or overtly, but subtly bent, as if the tracking speed fluctuated mid-exposure, or as if the stars themselves traversed arcs rather than straight paths. This phenomenon defies the expected behavior. Stars, relative to a properly tracking telescope, should maintain linear trajectories. If the tracking is amiss, the streaks should remain straight, merely skewed in their orientation.
Curved star streaks in the observation data present a significant puzzle. Such distortion could stem from non-uniform tracking, pointing towards a serious mechanical malfunction within the tracking system itself. Alternatively, it might indicate micro-movements of the tracked object, movements fundamentally inconsistent with the predictable, smooth orbital paths characteristic of comets. Comets follow well-understood trajectories dictated by solar gravity, their journeys marked by gentle curves, occasionally nudged by minor outgassing effects. These gaseous emissions create measurable but subtle perturbations, acting over extended periods of days or weeks to nudge the comet's position softly. Therefore, if the comet, designated 3/ATLAS, exhibited rapid wobbling or positional shifts sufficient to bend starlight into curves, this would represent an extraordinary and highly unusual phenomenon. It would imply the presence of forces acting upon the object that defy established physical models. Solar radiation pressure lacks the necessary strength, while outgassing torque would need to be impossibly violent. Furthermore, gravitational influences from nearby bodies are conclusively absent. No planets or asteroids exist in its vicinity, only the profound emptiness of space. Yet, despite this vacuum of plausible explanation, the star streaks demonstrably curve, creating a genuine observational challenge. Turning to the color data, Ray's imaging system utilizes an RGB sensor. This technology employs an array of red, green, and blue pixels, each sensitive to specific wavelengths of light. Their combined data constructs the full color composite image. Comets naturally display color variations within their coma, primarily influenced by the composition and size distribution of their ejected dust particles. Near the comet's core, where larger dust grains dominate, a reddish hue is common. This transitions outward to bluer tones further from the nucleus, where sunlight scatters more effectively off the smaller, more abundant grains, a pattern fully consistent with expectation. However, the observed sharp transitions and distinct unblended blue and green zones represent a stark departure from this norm. These abrupt color boundaries lack the smooth gradient anticipated from natural dust scattering processes, marking yet another unexpected anomaly in the data. Ray's photographs vividly illustrate this phenomenon. He captures distinct patches of color within the comet's poma, hues that defy explanation by a standard RGB camera setup observing reflected sunlight. These colors appear unnervingly saturated and sharply defined, almost resembling emission lines typically produced by specific gases. Crucially, Ray employed no narrowband filters. He did not isolate individual wavelengths. Therefore, the source of these unusual colors remains a puzzle.
Digital sensors inherently generate artifacts, particularly under challenging conditions like high ISO settings or during extended exposures. Overly bright, hot pixels may glow errantly, while cold pixels might fail completely. Furthermore, the process of bilinear interpolation used to fill gaps in the sensor matrix can sometimes fabricate false color gradients where none truly exist. If Ray's sensor was significantly noisy
and his subsequent image processing amplified this inherent noise. These mysterious color zones could be entirely artificial constructs. However, genuine sensor noise typically manifests as random, grainy chaos. The color patches observed in Ray's images, conversely, exhibit discernible structure. They align precisely with the bright points within the coma and follow the characteristic geometry of the coma itself. This structured response strongly suggests these features are reacting to something real within the captured scene rather than representing pure random noise. Potential explanations include dust particles with unusual compositional properties resting on the optical path, contamination affecting light transmission, or perhaps even the comet's coma genuinely emitting light in unexpected ways beyond the scope of typical cometary behavior. Crucially, Ray employed a specific image stacking strategy that forms another vital piece of this complex puzzle. He did not simply average his individual frames. Instead, he meticulously cropped each frame tightly around the comet's nucleus, aligned them with high precision, and then applied a nuanced approach to sharpening. He utilized light sharpening to enhance the overall structural integrity of the final composite image, while reserving significantly heavier sharpening to reveal the faintest, most delicate details emerging from the comet's diffuse envelope. This sophisticated processing technique contributes to the final appearance of those intriguing color features. Adjusting the image's contrast curves was the next critical step. This process involved selectively brightening areas that were initially too dark, while simultaneously scaling down overly intense highlights to fit within a standard viewing range. These procedures, while commonplace and technically sound, each carried inherent risks. Specifically, they could unintentionally magnify minor imperfections present in the original data. Applying sharpening techniques, for instance, might transform faint electronic noise generated by the sensor into what appears to be tangible surface detail. Similarly, altering contrast levels could cause random variations in brightness to manifest as seemingly coherent structures where none exist. Even minuscule misalignments between stacked images posed a threat, potentially generating ghostly duplicate features that appeared to trace elliptical paths around the primary object.
While image stacking offers significant advantages, it demands meticulous care. Without it, the process becomes perilous. The individual in question, much like many non-professional observers, prioritized achieving an aesthetically pleasing result rather than ensuring the utmost precision of the analysis. 3 specific images from this collection attracted particular scrutiny due to their depiction of structures resembling fireball-like tails extending behind the central object. These features differed markedly from the smooth, gradually fading tails characteristic of genuine comets. Instead, the tails appeared segmented, exhibiting distinct, almost lump-like segments projecting outward from the core. Some researchers proposed that these formations represented jet backflow, material expelled forward from the nucleus that subsequently becomes entangled within the solar wind and is redirected backward. Others suggested dust clumping as the explanation. This phenomenon occurs when microscopic particles collide and adhere, coalescing into larger aggregates that scatter light more effectively. Both mechanisms are scientifically plausible and observable in actual cometary activity. However, both processes typically generate disorganized, irregular patterns. The tails visible in these particular images, conversely, appeared excessively ordered and linear, evoking the impression of being deliberately pulled behind a moving entity, contrary to the natural, diffuse dispersion expected in space. Another potential explanation involves sharpening-induced blooming artifacts. The sharpening algorithm operates by accentuating boundaries, achieved by artificially increasing the contrast between adjacent pixels, which can sometimes create these deceptive linear features. Persistent halos or radio streaks may manifest near bright objects within an image when excessive sharpening is applied. These artifacts can bear a striking resemblance to genuine cometary tails, particularly in faint, noisy photographs.
While Ray's aggressive sharpening techniques could certainly generate such effects, the observed tails also appear, albeit faintly, in the less processed versions. Consequently, they cannot be attributed solely to sharpening. Their presence within the raw image stacks, though dimmer and less distinct, suggests another underlying factor, the possibility of oscillatory motion. If the comet, designated 3IATLAS, were rocking or yawing, its rotational axis shifting rhythmically as it spins, this movement would imprint repeating patterns onto stacked images. This motion would manifest as features seemingly pulsing or shifting in time, building up over numerous frames into apparent structure. This creates an illusion of internal order even if the comet itself exhibits chaotic behavior. Spacecraft experience this phenomenon directly. When a probe's attitude control is imperfect, a characteristic wobble occurs.
This periodic wobble is detectable in the spacecraft's telemetry data. The same physical principle applies to a comet nucleus subject to uneven torque caused by outgassing. The nucleus rocks, and its jets sweep back and forth. From a distance, this coordinated motion gives the impression of a structured system. This compelling illusion arises purely from the repetition of the motion. Professionals analyzing Ray's footage have employed a particularly insightful description: consistency in inconsistency. They refer to the observation that these anomalies lack randomness. The bright points do not flicker in and out arbitrarily, nor do the color zones shift chaotically. Instead, their behavior exhibits a discernible, non-random pattern. The anomalous curved star streaks manifest with deliberate regularity, appearing neither random nor haphazard. Their consistent repetition and inherent structure betray a discernible pattern, and such patterns invariably imply underlying mechanisms. Whether these phenomena stem from the inherent limitations of imaging technology and subsequent data processing, or represent genuine physical occurrences, remains a subject of ongoing investigation. Crucially, the fact that these strange distortions recur with measurable structure definitively distinguishes them from mere background noise. They constitute a meaningful signal. The pressing scientific inquiry then becomes, what specific phenomenon does this signal correspond to? Every astronomer possessing experience in capturing faint celestial objects has encountered moments where their equipment has produced deceptive artifacts mimicking genuine phenomena. Common culprits include micro-level imaging imperfections arising from amateur-grade instruments. Individual sensor defects, known as hot pixels, can cluster together. Unwanted light reflections, termed lens flares, sometimes appear in suggestive formations. Deliberately engineered optical features, diffraction spikes, can occasionally align in ways that create misleading impressions. The astronomical community is replete with cautionary tales. Luminous points revealed to be cosmic ray impacts, entire galaxies revealed as sensor glitches, and objects seemingly moving between exposures simply because the telescope experienced a minor vibration. Healthy skepticism is therefore not only warranted, but essential. Yet, inherent within this skepticism also lies fertile ground for curiosity. Consider this possibility. If the subtle positional shifts observed within the ray data are authentic, if the object genuinely exhibited unexplained wobbling, orientation changes, or possessed material in motion defying conventional cometary physics, the implications would be profound. We would then be confronting phenomena involving mass redistribution or jet-induced torque operating at intensities far exceeding standard theoretical expectations.
In the most speculative realm, this could even suggest the presence of an entity capable of actively controlling its trajectory. NASA's conspicuous silence regarding these developments, however, grows increasingly conspicuous with each passing day. Ray's footage achieved near instantaneous viral status. Within 2 days' time, it permeated countless online forums, social media platforms, and news aggregation sites. The agency must have become aware of this widespread attention.
Logically, they would have initiated investigations, deploying assets such as the Hubble Space Telescope, the James Webb Space Telescope, or at the very least directing ground-based observatories to conduct follow-up observations. Absolute silence now hangs over the anomalous observations. No official statement has been issued, no preliminary data released, and certainly no press conference delivered to reassure the public that the findings are merely artifacts or explainable by natural phenomena. This profound silence acts as fertile ground for rampant speculation. The fundamental question lingers. If there is truly nothing unusual to observe, why not simply declare it? Why not immediately release images depicting a perfectly ordinary comet exhibiting standard jet activity, thereby settling the matter decisively? Unless, of course, their own observations reveal a similar perplexing pattern. Unless their data confirms the ray-like structure detected. Unless their team is currently grappling with how to interpret these results without invoking a major media frenzy. The suspicious timing only accelerates the spread of doubt. The paramount question keeping many awake is, what do the scientists already know? Do they possess spectroscopic data suggesting an unusual composition within the comet? Do they have access to high-resolution imaging that reveals intricate structural details within the nucleus? Do they have radar returns indicating an unexpected shape or rotational pattern? Or do they, in fact, have precisely what independent observers like Ray detected, just with clearer, more definitive imagery? And are they now staring at this evidence with the same mixture of awe and apprehension we feel, desperately weighing whether the universe has just presented them with something truly extraordinary, or whether an embarrassing artifact is about to be exposed? The answer remains unknown, and in this state of uncertainty, the lack of information proves far more unsettling than almost any conceivable revelation. The unresolved tension preceding the NASA flyby, the specific timing, the noticeable delays, the withheld data will be our next focus. Because if this mystery is destined to erupt into public view, it will likely commence right here, within this silence, within the deliberate omissions, within the vast chasm between mere observation and any meaningful explanation, where possibilities proliferate unchecked. This is where the unraveling begins.
The protocols governing how space agencies share information follow a distinct rhythm. An intriguing phenomenon is spotted. A specialized instrument is deployed to observe it. Data is gathered, preliminary analysis is conducted, a concise summary is prepared. Finally, a formal statement or press conference is held. The entire journey from initial observation to public announcement usually spans several days, potentially extending to a week if the data proves particularly complex or necessitates peer review. Each step involves a calculated communication strategy. Announcing the findings serves a vital public relations function. It offers reassurance to the public, demonstrating that trained experts remain firmly in charge, that even the most enigmatic aspects of the universe are under systematic observation and actively being understood. Consequently, when NASA falls silent, effectively breaking this established rhythm, the absence becomes immediately noticeable. People naturally wonder why. Ray's footage spread with remarkable speed. Within 48 hours of his initial post, it had been shared thousands of times across various platforms. By the 72nd hour, mainstream science-focused media outlets had begun reporting on it. Amateur astronomers worldwide simultaneously trained their telescopes on the 3 designated locations attempting to replicate his findings. Results were mixed. Some succeeded in capturing similar patterns, others detected faint echoes of the same configuration, while many observed nothing out of the ordinary. This inconsistency only intensified the ongoing debate. Yet one voice remained strikingly absent: NASA's. There was no social media update, no blog entry, not even a preliminary acknowledgement stating, "We are aware of the amateur footage and are investigating." Just a profound silence. In today's world of instant communication, such deliberate quiet feels particularly significant. Normally, NASA responds with notable speed. When Oumuamua was first spotted in 2017, the agency promptly released key information within days, including orbital parameters, preliminary size estimates, and reflectivity measurements.
In 2019, when Boris appeared, they followed the same protocol. They confirmed its interstellar origin almost immediately and provided regular updates as it traversed the inner solar system. Their transparency and engagement during these discoveries made the public feel included in the process. However, with 3IATLAS, something has changed. The object was detected and its interstellar trajectory was confirmed, but then there was silence. A scheduled briefing was announced, only to be postponed, rescheduled, and postponed again. Officials cited ongoing analysis and data calibration as reasons, which seemed like routine excuses. But these excuses fall flat when amateur astronomers are capturing and sharing real-time images.
Meanwhile, the agency, responsible for some of the most advanced telescopes in existence, has nothing to share. If you believe the rumors, internal chatter tells a different story. People with connections inside the Jet Propulsion Laboratory or the Space Telescope Science Institute whisper about early Hubble images revealing structural anomalies in the object, features that shouldn't be there, patterns that match what Ray captured, but with higher resolution and better signal-to-noise ratios. These are just rumors, unconfirmed, the kind of stories that spread on forums and through private messages among enthusiasts who know people who know people. Persistent whispers continue to circulate, their specificity suggesting either genuine discovery or exceptionally crafted fabrication. These accounts specifically allude to image processing pipelines adept at identifying geometric forms within cosmic data. They reference internal communications where agency staff debated the classification of certain observations as potential artifacts, pending further scrutiny. The rumors further describe internal deliberations, where scientists meticulously weighed how to communicate findings without immediately provoking intense speculation regarding artificial origins. Crucially, no concrete evidence of deliberate concealment exists. There is no definitive proof. No whistleblower has surfaced with classified imagery. While NASA typically operates with considerable transparency, bound by policies mandating public access to research funded by public dollars, such directives inherently contain exceptions. Data may be temporarily withheld if premature release risks undermining scientific rigor. This precaution applies when concerns exist about potential artifacts, the likelihood of misinterpretation, or the risk of causing unnecessary public alarm over phenomena that ultimately prove mundane. In such circumstances, the agency possesses the authority to exercise patience. They can extend timelines significantly, ensuring that any eventual public statement presents conclusions that are thoroughly validated and beyond reasonable doubt. However, this necessary delay creates a vacuum where speculation naturally flourishes. Each passing day without clarification allows conspiracies to gain incremental strength. Questions posed by the public become increasingly pointed, and trust in the institution experiences a corresponding erosion. It is important to note that legitimate explanations for extended processing times do exist. When analyzing faint, distant celestial objects, the complexity of data processing presents significant hurdles. Raw images captured by powerful telescopes are notoriously noisy, plagued by cosmic ray interference, scattered light, and various instrumental artifacts.
Careful calibration, precise background subtraction, accurate frame registration, and proper stacking techniques are all essential steps in transforming this raw data into scientifically reliable information. Experienced image processors caution that hasty releases often yield visually striking results that ultimately prove misleading, merely representing amplified noise rather than genuine celestial phenomena.
The Space Agency learned this difficult lesson during the initial operational phase of the Hubble Space Telescope. Expedited publication of uncalibrated imagery resulted in significant public relations challenges when the telescope's optical flaw became publicly apparent. Since that period, the organization has adopted a markedly more deliberate approach to public disclosures. The core principle guiding this methodology emphasizes accuracy over speed. It is preferable to proceed slowly and ensure correctness than to move quickly and risk inaccuracy. This official rationale appears sound until one considers the achievements of an independent observer utilizing only improvised equipment and fundamental image stacking software. His creation of compelling visuals capable of rapid viral dissemination within a single weekend period prompts a natural question. If such results are attainable in a matter of days, why might a major organization require 2 weeks? A critical factor demanding this extended timeline is the necessity for multi-wavelength confirmation. Professional astronomers analyze celestial objects across numerous segments of the electromagnetic spectrum, not solely within the visible light range. Obtaining infrared data is essential to measure thermal signatures and dust emissions. Ultraviolet observations are required to detect specific gas fluorescence patterns. Spectroscopic analysis must be conducted to identify distinct molecular compositions. Furthermore, if the astronomical object is sufficiently proximate, radar return data provides invaluable information. Assembling this diverse array of observations, synchronizing data collection across multiple observatories, and meticulously synthesizing the complex results constitute a time-intensive process. This is not a matter of indolence, it represents scientific rigor. The objective is unequivocally to achieve a comprehensive understanding before presenting any conclusions publicly. Determining whether the bright points captured by the independent observer manifest in infrared data is crucial. Their appearance in infrared wavelengths confirms thermal emission, indicating their physical reality. Conversely, their absence suggests they may be mere optical artifacts. This fundamental distinction separates a legitimate discovery from a potential source of embarrassment. Consequently, the space agency exercises patience, gathering data methodically and conducting thorough analysis.
Meanwhile, the public, observing the elapsed time with growing anticipation, experiences increasing impatience. The critical task of noise filtration cannot be overstated. Major space observatories, such as Hubble and the James Webb Space Telescope, generate staggering volumes of observational data amounting to thousands of terabytes per session. The vast majority of this information constitutes non-essential data. Sources include thermal interference, readout inaccuracies, and stray photons that don't originate from the target celestial body. Sophisticated automated processing pipelines are employed to eliminate this background clutter. However, these pipelines operate with notable caution. They tend to err on the side of removing any element exhibiting potentially anomalous characteristics. Should the object designated 3II/Atlas contain faint structures registering as unusual, the pipeline might categorize them as instrumental artifacts and exclude them from the finalized imagery. Subsequently, astronomers would be compelled to undertake a meticulous manual inspection of the unprocessed data sets. This involves identifying precisely what filtering mechanisms have discarded, followed by a rigorous assessment to determine if the discarded signals represent genuine astrophysical phenomena. This verification process is inherently time-consuming. It necessitates comparative analysis across multiple observations, complex simulation modeling, and consultation with specialist researchers. The endeavor represents science conducted at its most painstakingly detailed level. Yet, from an external perspective, it can appear as evasive behavior or reluctance to acknowledge findings promptly. What are NASA's primary reservations regarding such situations? Mitigating the risk of another highly publicized unidentified aerial phenomenon, unidentified object media frenzy, undoubtedly ranks prominently among their concerns.
The object known as Oumuamua ignited intense debate that persisted for years. Astrophysicists engaged in prolonged discussion over the potential causes for its peculiar acceleration: outgassing of volatile materials, the subtle push exerted by radiation pressure, or, less conventionally, the possibility of an artificial origin. The concept of a light sail directly entered scientific discourse. A distinguished astronomer formally hypothesized it might be of artificial design. The global media landscape seized upon this possibility. Headlines captured widespread public attention, speculating openly about potential extraterrestrial probes. NASA subsequently invested months carefully retracting the more speculative interpretations, presenting comprehensive datasets and theoretical models demonstrating that natural phenomena provided sufficient explanations. This experience was profoundly exhausting.
It diverted significant resources and focus away from other critical space missions and established a problematic precedent, revealing that interstellar objects frequently provoke reactions disproportionate to their scientific significance. Should 3I/Atlas exhibit even the faintest suggestion of the unusual, the agency would be thrust into a highly charged scenario. They would face direct questions regarding its artificial origin. Pressure would mount for them to address the escort hypothesis explicitly. Every single statement made would be subject to intense scrutiny. Every photograph and video frame would be dissected by countless self-proclaimed experts online, each searching desperately for evidence supporting their preconceived theories. The situation presents a clear no-win proposition. The inevitable response becomes delay. They would engage in exhaustive verification procedures, triple-checking all findings. Simultaneously, they would meticulously craft their official messaging and strive to shape the unfolding narrative before it inevitably takes on its own life. Public psychology significantly influences this dynamic. Silence, after all, creates a void, and such a void naturally gets filled with fear, wonder, and boundless human imagination. People possess a powerful tendency to project their own deepest hopes and anxieties onto the realm of the unknown. Within the public, two distinct camps emerge. Some fervently desire 3I/Atlas to represent something profoundly extraordinary, evidence of first contact, a probe dispatched from another civilization, tangible proof that humanity is not alone in the universe. Conversely, others desperately wish it to be revealed as entirely mundane, merely a comet or asteroid passing by, presenting absolutely nothing to be concerned about. Both of these opposing groups remain intensely focused on NASA's responses, seeking validation for their own perspectives. NASA, acutely attuned to this complex social dynamic, understands that whatever official position they adopt will inevitably satisfy one audience while provoking the other. Declaring the observed anomalies as definitive artifacts would immediately invite accusations from believers of a cover-up, a suppression of the true nature of 3I/Atlas. Conversely, acknowledging the reality of the patterns while admitting their current unexplained status would likely trigger demands for instant answers from skeptics, who would then criticize NASA for lacking clear explanations. There exists no perfectly acceptable resolution path within this dilemma. The only viable course becomes managing the fallout, damage control. Internal discussions would likely reflect this profound complexity, featuring arguments such as one faction insisting releasing the available data, even if it remains incomplete, is the necessary step. Transparency fosters public trust. We should present what we possess.
We should clearly outline the uncertainties and invite the broader scientific community to contribute their expertise and analysis. A distinct perspective advocates for restraint. They argue to await conclusive evidence before engaging publicly. Speculation, they warn, should not be encouraged. Furthermore, they believe fueling theories provides unnecessary material for those seeking hidden agendas. Both viewpoints presented possess defensible reasoning. Historical examples substantiate each stance. It is probable that this very debate unfolds within strategy sessions at facilities like Goddard and JPL, where astronomers and mission planners deliberate. This underlying friction between the drive for scientific transparency and the need for institutional prudence is genuine. It carries no malicious intent. Instead, it emerges from the inherent structure and responsibilities within large research organizations. Yet, from an external viewpoint, this cautious approach can appear evasive, creating an impression of concealment. Distinguishing between a genuine cosmic structure and an observational artifact proves genuinely challenging. One cannot simply examine an image and achieve certainty. Reliable analysis demands multiple, independent observations gathered from diverse vantage points, utilizing different detection instruments, and spanning various time periods. Scientists must meticulously model how potential artifacts might propagate through complex data processing pipelines. They need to create simulations depicting what the object should appear like under a range of plausible assumptions, then rigorously compare these models against actual observations. A match between simulation and reality offers a strong indication. However, any significant discrepancy necessitates deeper investigation. Researchers then methodically scrutinize for potential instrumental effects or external environmental factors such as reflected moonlight or atmospheric distortion. Only after systematically eliminating every mundane, conventional explanation should more extraordinary possibilities be entertained. This meticulous process embodies the scientific method, albeit a notably deliberate one. The critical challenge arises from the object's trajectory. It is receding rapidly from our solar system, racing back towards the vast emptiness beyond. Consequently, time becomes an increasingly scarce resource. Each passing day renders the object fainter and its observations more difficult. With every week that passes, the practical window for study narrows further. The inexorable passage of time creates a tangible pressure. NASA is acutely aware of this Jin-Pol-theory reality. The central question burning fiercely in everyone's mind: do Hubble or the James Webb Space Telescope capture images displaying the same distinctive five-point pattern? The outcome hinges critically on the appearance of the coma structure.
Should these powerful observatories reveal smooth, asymmetric comae devoid of any bright, distinct nodes, the entire mystery would effectively dissolve. In that scenario, Ray's footage would stand as a stark, cautionary tale illustrating the potential pitfalls of amateur image processing techniques. However, the narrative shifts dramatically if Hubble or JWST discern the identical pattern, or worse, presented with even greater clarity. Then the nature of the discourse undergoes a fundamental transformation. The debate ceases to be a simple question of reality versus illusion, pivoting instead towards the profound inquiry: what could this phenomenon possibly be? This constitutes a significantly more complex and challenging conversation. Once the pattern's existence is conclusively confirmed, the imperative to provide an explanation becomes inescapable. What follows, as previously explored, is a progression towards increasingly specific and unlikely conditions and coincidences. The spectrum of natural explanations begins to resemble artificial ones in their perceived contrivance. This intricate and unsatisfactory situation represents NASA's deepest concern. Their fear is not that the 3-to-1 ratio is artificial, but rather that they may be utterly incapable of definitively demonstrating that it is not.
This perceived inability to provide a conclusive rebuttal fosters an environment where speculation inevitably flourishes. The discourse extends well beyond fringe theories. Instead, serious individuals, including professional astronomers affiliated with major universities, begin initiating their own independent observing campaigns. Simultaneously, data scientists are actively petitioning for access to publicly available archives, seeking the opportunity to conduct their own rigorous analyses. Journalists, sensing an unfolding story, are diligently investigating, making discreet inquiries, and attempting to locate sources willing to speak off the record. The cumulative effect of these actions creates mounting pressure that steadily accumulates. This pressure will inevitably reach a critical threshold. Consequently, NASA will be compelled to issue an official statement. A formal briefing will occur, accompanied by the release of pertinent data. Ultimately, we will gain clarity on whether the escort hypothesis possesses any foundation in reality, or whether Ray's observation was, in fact, the product of a perfectly improbable confluence of artifacts that managed to deceive the entire scientific community. The tension finally dissolves. Yet until that moment, we remain suspended in wonder, captivated by 5 faint points in an amateur photograph, gazing upward with the fundamental question that shapes our cosmic perspective. Are we witnessing nature operating at its most extraordinary, or intelligence expressing itself at its most refined?
And which revelation would prove more profoundly unsettling? We now delve deeper. We examine the escort hypothesis thoroughly. If those points were genuine entities, what configuration could possibly align with the data? What physical arrangement could generate the pattern observed by Ray? This constitutes a thought experiment, a carefully constructed what-if scenario. Yet, such mental exercises possess a unique power. They illuminate possibilities previously unconsidered, and occasionally, those very possibilities mirror reality. This is part 6, the escort hypothesis. If it were genuine, what specific configuration would fit the observed data? Let us embark on a conceptual journey. Let us, for the next 1,000 words, entertain the substantial assumption that Ray captured something authentic, that the 5 bright points represent neither artifacts of the image nor optical illusions or misinterpreted cometary debris, but are indeed discrete objects or structures. These entities maintained fixed positional relationships relative to the comet's nucleus as it rotates and journeys through the void. It is a significant assumption, perhaps ultimately incorrect. However, assumptions serve as vital tools for exploration. They allow us to chart the landscape of possibilities. They empower us to ask, if this premise holds true, what form would it take? What physical principles would be required? Which configurations demonstrate logical coherence? And crucially, what specific observations would confirm or refute this scenario? Let us investigate the escort hypothesis not as proponents, but as critical observers. We shall trace its logical implications and assess its resilience under scientific examination. First, considering the geological plausibility. Cometary nuclei are known to fragment through various mechanisms: tidal forces exerted by massive bodies, internal thermal stresses generated by solar heating, or even rotational instability can all cause a comet's core to split into multiple pieces. Therefore, if Comet 3I/ATLAS experienced such a fracture event during its history, the resulting fragments could theoretically still be journeying through space as a related group, loosely bound by their mutual gravity. Observationally, this would manifest as several distinct bright points dispersed across the sky. Each fragment, reflecting sunlight, would contribute to a shared, diffuse atmosphere, the coma. The specific spacing between these points would depend entirely on the timing of the breakup and the nature of the forces involved. However, a significant challenge arises from gravitational interactions.
Between closely orbiting fragments, these interactions inevitably alter their trajectories over time. The pieces would gradually drift apart due to orbital perturbations, or conversely, risk collision. Sustaining 5 identifiable fragments in a stable, ring-like configuration throughout the extended period it took 3IATLAS to traverse interstellar space demands exceptionally precise initial conditions. While physically possible, achieving such a configuration by chance is considered highly improbable. Furthermore, such a tight group of fragments orbiting a common center would be expected to exhibit periodic fluctuations in overall brightness. These variations would occur as fragments periodically eclipse one another or alter their relative phases with the Sun. Crucially, the observed 5 points maintained relatively constant brightness levels over time. This lack of observed periodic fluctuations represents a significant challenge to the fragmentation hypothesis. Turning to the alternative explanation involving symmetric vent positions, imagine a comet nucleus possessing 5 distinct active regions distributed evenly around its equatorial belt. As this comet approached the inner solar system, solar radiation would heat these specific locations. Each active region, or vent, would then become intensely heated, triggering the ejection of material, a combination of dust and gas, forming prominent jets or plumes. From our vantage point, these plumes seem to be discrete points encircling the comet's nucleus. This is entirely logical. It doesn't necessitate any exotic explanations. However, it does require the nucleus to have a specific form and structure. The vents must be positioned at approximately 72 degrees apart, and they must activate almost simultaneously or in rapid succession, so that they all appear active in one image. Moreover, the dust they eject must scatter light effectively towards us. This presents several conditions. While not impossible, these requirements are quite stringent. The question then arises, how did the nucleus develop such symmetrically placed vents? Random accretion over billions of years wouldn't yield regular patterns. Collisions typically introduce chaos rather than order. Therefore, if the vents are genuine, some force must have shaped the nucleus deliberately. Even if this shaping was purely geological, the outcome appears designed.
While extending the concept of three-dimensional ice or atlas crystalline order to a comet-sized body would necessitate the entire nucleus possessing long-range molecular order, scientific consensus holds that cometary nuclei are instead loosely bound aggregates, effectively rubble piles composed of icy and rocky fragments. Such structures are fundamentally incompatible with being single, monolithic crystals. Nevertheless, if an ice body forming under highly unusual conditions, perhaps within an environment characterized by intense magnetic fields, or exhibiting exceptionally slow, controlled accretion processes, could theoretically develop an atypical internal architecture. While such a structure seems highly improbable, it cannot be categorically ruled out. Conversely, plasma-based explanations enter significantly more speculative territory. Plasmas possess the inherent capacity to form complex structures, and magnetic fields are capable of trapping charged particles within remarkably stable configurations. Laboratory experiments have indeed demonstrated the creation of self-contained plasma knots and toroidal, donut-shaped configurations, structures exhibiting persistence far exceeding expectations for typical random ionized gas. Could analogous phenomena occur within a comet's diffuse coma? If the comet is actively ejecting ionized material, and if a magnetic field is present, potentially generated locally or arising from interactions with the solar wind, the plasma could theoretically organize into discrete luminous nodes. These nodes would emit light as ions recombine or electrons release photons, appearing distinctly bright. Furthermore, if the magnetic field geometry proved sufficiently favorable, these glowing nodes might arrange themselves into discernible, symmetric patterns.
The principal obstacle lies in the inherently weak magnetism associated with comets. Their nuclei, composed primarily of ice and rock, possess no significant intrinsic magnetization akin to magnetized iron. While the solar wind provides a background magnetic field, its strength at the relevant distances is notably feeble. Achieving stable plasma structures within a comet's environment would therefore require conditions markedly different from those normally observed or expected in cometary systems. While not categorically impossible, this phenomenon remains highly unusual. It would necessitate physical principles operating at the very frontier of our comprehension regarding cometary environments. The concept of photonic resonance itself carries even greater theoretical uncertainty. Nevertheless, the creation of force by light is an established physical reality. Radiation pressure is demonstrably real and measurable. Photons, indeed, convey momentum. When these particles reflect off or are absorbed by material, they exert a push.
In theory, if dust particles within the comet's surrounding envelope possessed the correct dimensions and composition, they could potentially form stable arrangements. In such configurations, the outward force generated by sunlight radiation pressure might balance the inward pull of gravitational attraction. These hypothetical stable points could be termed photonic resonance zones, locations where solar light generates stationary wave patterns within the dust distribution. The characteristic geometry of these formations would likely depend on complex spatial relationships, possibly resulting in symmetrical structures. This idea has been suggested theoretically for other cosmic systems, yet it has never been confirmed through direct observation. Extending this concept to comets requires the dust to possess exacting characteristics and the sun's radiation to interact with the coma in ways that appear meticulously balanced. It is not entirely impossible, but rather statistically improbable. Furthermore, its existence raises a significant question. If such resonant structures were present, why have they not been observed in other comets? Conversely, astronomically grounded mechanisms offer more plausible explanations. Smaller fragments ejected during a previous disruption of the comet core could readily generate the pattern identified by Ray. If the comet experienced a violent fragmentation event at some point in its history, forcefully expelling material at specific velocities, portions of this debris could find themselves captured in orbit around the surviving central body. The subsequent motion of these fragments would then be governed by the fundamental principles of orbital mechanics. Depending upon the mass distribution and rotational characteristics of the comet nucleus, stable orbital paths could indeed emerge. The fragments would orbit the nucleus, holding remarkably stable positions within the comet's rotating perspective. This phenomenon stems from genuine physics, mirroring celestial mechanics observed elsewhere. Moons maintain orbits around planets, while planetary rings encircle gas giants. Identical principles operate at vastly reduced scales. However, comet nuclei represent minuscule bodies. Their gravitational pull proves exceedingly weak. Sustaining 5 distinct fragments in stable orbit would necessitate an unnervingly close proximity, practically grazing the comet's surface. At such minute distances, the subtle resistance posed by the comet's surrounding atmosphere, known as the coma, would inexorably slow the fragments. This atmospheric drag would trigger orbital decay. The fragments would progressively spiral inward, ultimately impacting the nucleus. Such a configuration could not endure. The only potential resolutions lie in an external mechanism continuously restocking the fragments, or a significantly lower than anticipated coma density.
Absent these factors, orbital mechanics presents considerable difficulty in accounting for such prolonged stability. This leads to Part 7, reconstructing the comet's three-dimensional movement from amateur observations. You are observing a spinning comet situated millions of miles away. Peering through a telescope susceptible to slight wobbling with every passing breeze, you capture dozens of exposures, meticulously stacking them, then sharpening the composite result. Suddenly,
an arrangement emerges that eluded initial observation. 5 distinct, bright points forming a ring, exhibiting movements that appear coordinated. The core question posed by all observers remains deceptively simple. Are these points rotating in concert with the comet itself, or are they dynamically orbiting it? Ray's images deny us the cinematic luxury of a 360-degree fly-around view. Instead, we confront a flat, two-dimensional projection of a three-dimensional object executing a complex choreography within the profound darkness between the stars. Nevertheless, scientists possess ingenious techniques for deciphering motion from seemingly flat images. Certain analytical techniques remain effective even when working with less precise, amateur-grade observational data. One fundamental method involves examining differential luminosity. While the terminology may sound complex, the underlying principle is remarkably simple. By systematically comparing the brightness of individual features across successive image frames, researchers can begin to discern their positional changes relative to the comet's central nucleus. If all observable points consistently increase and decrease in brightness simultaneously, they likely represent features firmly attached to the nucleus itself. Their fluctuating visibility governed solely by the changing angle of sunlight illuminating potential jets or vents. Conversely, if these points exhibit independent, sequential brightening, resembling the rhythmic glow of Christmas lights encircling a tree, they likely constitute separate orbiting objects. Observations of comet 3IATLAS reveal a scenario falling somewhere between these two extremes. The points do not pulse in perfect synchrony, yet they fail to follow a neatly ordered sequence. The pattern is more intricate than simple periodicity, displaying a distinctly organic complexity. This could stem from the comet's rotation axis being tilted relative to Earth's line of sight, generating a convoluted illumination pattern as varied surface features periodically rotate into and out of view. Another valuable technique is coma backscatter analysis. The surrounding dust cloud, often perceived merely as visual ornamentation, actually serves as a powerful diagnostic instrument. Sunlight striking dust particles within the coma partially reflects or scatters back towards Earth.
By meticulously analyzing which specific regions within this diffused cloud exhibit the greatest brightness, researchers can deduce the orientation of the hidden nucleus. If the nucleus is a spinning body ejecting material, the pattern of backscattered light within the coma will shift in predictable ways as different hemispheres of the nucleus successively face the Sun. Examination of Comet 3I by Atlas's coma reveals subtle yet significant shifts in brightness distribution, providing compelling evidence that the object is indeed rotating. The observed period appeared remarkably brief, far shorter than expected for a typical comet nucleus. While most comets exhibit rotation cycles spanning several hours, with some requiring days, the transformations detected by Ray occurred within an astonishingly compressed window of just 60 to 90 seconds. This rapid change suggested two possibilities: either an unusually swift rotation rate, which would be highly atypical for an object possessing sufficient mass to sustain a coma, or a phenomenon known as precession. This wobbling motion, reminiscent of a spinning top beginning to topple, can create perceptual illusions. Specifically, a slowly rotating body undergoing precession can seem to alter its orientation dramatically faster than its actual rotational speed would indicate. This effect arises from the superposition of two distinct rotational motions occurring simultaneously at different rates. The analogy of a wobbling football appearing to spin faster than it truly is illustrates this principle effectively. However, a perplexing anomaly emerged.
If the 5 observed points were fixed elements attached to the nucleus itself, locked into specific surface features such as vents or craters, then their movement during rotation should follow predictable, sweeping arcs. Their relative positions should shift significantly, potentially overlapping as the nucleus turned. Instead, these points defied expectation. They maintained their consistent spacing and remained distinctly in formation. This remarkable persistence is the primary reason the escort hypothesis continues to hold scientific interest. Consequently, some researchers proposed an alternative explanation. The points might not be surface features at all. They could instead be discrete clumps of dust trapped within stable orbits and circling the nucleus. These particles would be held in place by the delicate balance between the comet's weak gravitational field and the thrust generated by outgassing jets. This orbital trapping mechanism, termed a trace-idle path, occurs when particles become ensnared in repeating, looping trajectories. They spiral around the nucleus, but neither escape into deep space nor precipitate back onto its surface. The underlying mathematics proves feasible. Within specific size parameters, microscopic particles can indeed remain suspended in near-stable orbits encircling an active comet nucleus.
These particles would manifest as luminous points against the backdrop, their brilliance stemming from reflected sunlight, while the nucleus itself, shrouded in relative darkness, remains less conspicuous. Furthermore, if the comet possesses a rotational axis, these orbiting particles might preserve their spatial configuration relative to the nucleus, provided their orbital velocity exceeds the comet's rotational speed. However, a significant challenge emerges regarding the observed phenomenon, the formation of a symmetric ring composed of precisely 5 distinct dust clumps, maintaining this arrangement over time. Such perfect symmetry defies easy explanation through gravitational forces alone, which lack the mechanism for such precise, evenly spaced positioning. This configuration seemingly demands either an improbable alignment of circumstances or the influence of an additional organizing principle. Potential explanations might involve the presence of electric fields within the comet's surrounding coma. Alternatively, if the nucleus retains any residual magnetism, complex magnetic field structures could theoretically sculpt the dust into this symmetric pattern. Conversely, the observed symmetry might be entirely an artifact of the specific image processing techniques employed by researcher Ray. Furthermore, expertise in cometary dynamics, particularly analysis of the comet-designated 67P during the renowned Rosetta mission, reveals the profound complexity inherent in cometary spin states. The Rosetta mission subject exhibited chaotic tumbling, its rotational orientation shifting unpredictably over time due to asymmetric outgassing. The powerful jets erupting from one side of the nucleus generated torque, functioning analogously to tiny thrusters that progressively altered the body's orientation. If Comet 3IATLAS is undergoing a similar process of rotational change even as it is observed, this inherent dynamism could complicate interpretation. Ray's collected data, therefore, cannot provide conclusive evidence definitively categorizing the 5 observed points as surface features, fragments engaged in orbit, or simply optical illusions. The limitations are clear. The observational resolution lacks the necessary sharpness, and the temporal coverage is insufficiently prolonged. Nevertheless, the data undeniably points towards the underlying reality of the comet's environment being far more intricate than initial appearances might suggest. The observation suggests something far more complex than a mere tumbling rock. This very possibility is what makes the discovery so compelling. Consider this hypothetical. If those 5 distinct points genuinely existed as objects traveling in orbit around the comet's core, their incredibly rapid movement could be used to calculate their orbital period.
By analyzing the shifts between consecutive images, one could deduce that such objects would need to complete a full revolution astonishingly quickly, approximately every 3 to 5 minutes. This speed is staggering. Achieving such rapid motion would force any orbiting fragments to remain perilously close to the nucleus, only a few dozen meters away. Any greater distance would see the centrifugal force overcome the comet's feeble gravity, hurling the fragments out into space. Could small fragments truly orbit a comet nucleus at such blistering speeds? Perhaps, if the core itself were extraordinarily dense and the fragments minute enough, though this scenario pushes the boundaries of physical plausibility. This places us at a fascinating crossroads. Either we are witnessing an extremely rare and unusual natural phenomenon, or perhaps something entirely different is at play. Until astronomers direct significantly more powerful telescopes towards Comet 3IATLAS and track these points steadily over hours rather than the brief minutes captured so far, this mystery will persist. Yet it remains profoundly significant that data gathered by dedicated amateurs brought us this remarkably close to an answer. Looking back at the history of astronomy reveals a pattern. Amateurs have repeatedly outperformed professionals. Professional astronomy operates on an immense scale. Telescopes stand as colossal structures, dwarfing ordinary buildings. Sophisticated computers run calibration algorithms honed over decades. Entire teams of scientists spend their careers mastering techniques to extract meaningful signals from overwhelming noise. One might assume such formidable resources leave no room for surprise. History, however, proves otherwise, demonstrating that unprecedented discoveries often emerge from unexpected quarters.
Professionals, reassured by their initial data, reviewed their archived records. They found the faint fragment there, too, nestled in their own captured light. Yet their automated filters had already marked it as an artifact of the instrumentation and removed it from consideration. The critical insight belonged to the amateurs. Driven by raw curiosity and a willingness to challenge the algorithms, they examined the unfiltered data directly with their own eyes. They noticed subtle features dismissed as imperfections, evidence of something truly present. Similarly, consider July 1994. Comet Shoemaker-Levy 9, on a collision course with Jupiter, was poised to become one of the most intensely observed astronomical spectacles in human history. Professional observatories meticulously calculated the exact timing and location of each anticipated impact with pinpoint precision. Despite this, amateur astronomers scattered across the globe captured a detail overlooked by the large automated survey scopes. Faint, trailing fragments forming a chain beyond the main body were visible in their carefully compiled images. These pieces were simply too dim and diffuse for the professional systems designed to detect only brighter objects. Yet they were plainly visible to dedicated observers willing to invest the necessary time. Patient astronomers painstakingly stacked dozens of individual exposures by hand, merging faint signals across multiple photographs to reveal the hidden structures. These dedicated individuals captured evidence of the comet's disintegration that the vast professional resources focused on the main event had missed. The fragments proved authentic. Strikingly, some struck Jupiter hours after the primary impacts, triggering secondary fireballs that defied prediction. Shifting focus to Comet 17P Holmes in October 2007 offers another compelling instance. This typically faint celestial object underwent a dramatic, sudden brightening, becoming naked-eye visible within a single night. It was amateur astronomers who first documented the expanding debris cloud in detail, revealing intricate structures within the outburst, radial jets, and spiral patterns that strongly indicated the nucleus was rotating and ejecting material in organized streams.
By the time professional observatories redirected their powerful instruments towards the phenomenon, the initial explosive phase had already progressed significantly. The dedicated amateurs had captured the critical early phase, the zenith of chaotic activity, precisely because they maintained constant vigilance. The professionals, constrained by scheduling and planning, found themselves scrambling to gather data after the most dynamic moments had passed. Why does this recurring pattern occur? How do observatory-equipped backyard enthusiasts consistently outpace multi-billion-dollar facilities?
Part of the explanation lies in sheer observational coverage. Thousands of passionate amateur astronomers, distributed globally, observe the skies every clear night. Their pursuits operate independently of telescope allocation committees or rigid grant funding cycles. Should an unexpected celestial event emerge, they can immediately direct their commercial-grade instruments towards it. The process involves no formal proposals, no time-consuming peer review, simply pure curiosity, compelling them to capture whatever photons reach their detectors without delay. However, another crucial factor stems from the fundamental differences in data handling philosophy. Professionals routinely apply standardized processing pipelines, meticulously designed to yield clean, publishable images. These techniques involve aggressive noise reduction, flat field correction, and artifact removal. While effective for producing polished final outputs, this very process of refinement can sometimes inadvertently discard or smooth over the subtle, fleeting details characteristic of transient astronomical events, details often preserved in the raw, unprocessed data initially captured by persistent amateurs. Smooth cosmic appearances naturally pass through astronomical image filters. This initial screening usually proves effective. The vast majority of peculiarities encountered within astronomical photographs are indeed mere noise, although this isn't an absolute rule. Many amateur observers, particularly those who meticulously process their own visual data, frequently bypass such stringent filtering. Instead, they employ gentler image stacking techniques and experiment with varied sharpening kernels. Their primary objective rarely involves generating data suitable for formal scientific publications. Their aim is often simply to discern the genuine content of the image, artifacts included. Within this intricate noise, however, genuine celestial phenomena can sometimes be concealed. Ray's photographic record of the 3IATLAS objects exemplifies this approach precisely. His choices during the image stacking phase were notably unconventional. He favored tight crops and applied moderate sharpening, deliberately avoiding the rigorous noise suppression methods typically utilized by professional analysts. This critical difference in processing methodology is precisely why the 5 distinct points became discernible in his images. A standard professional pipeline, with its emphasis on smoothing, would likely have eliminated these features along with suspected artifacts. Does their visibility in his images definitively confirm their reality? Not definitively. It indicates only that they possess a persistence robust enough to withstand the specific processing techniques Ray employed. A fascinating observation, yet insufficient proof alone.
The inherent risk associated with amateur discoveries lies in the potential introduction of artifacts that appear highly convincing, yet lack physical reality. Examples include effects stemming from rolling shutter mechanisms, minor tracking inaccuracies, sensor blooming effects, or the presence of persistent hot pixels that coincidentally align across multiple captured frames. Although these elements can coalesce to generate structures that appear deceptively organized, seeming too structured to be random chance. Professional processing pipelines specifically target and remove these artifacts to prevent misleading discoveries. Consequently, the situation necessitates careful, focused attention. While professionals often overlook subtle phenomena, amateurs possess a distinct advantage. They perceive both genuine anomalies and perceptual artifacts. The critical challenge lies in discerning the difference, demanding meticulous analysis, independent verification, and considerable patience. Ray's experience exemplifies this dynamic. Verification efforts are now underway, with numerous amateur astronomers directing their telescopes towards 3IATLAS, attempting to replicate his findings. Observations vary significantly. Some witness the distinctive 5-point formation, while others detect none at all. Reports even describe configurations with 6 points, 4 points, or a continuous ring. This divergence underscores how profoundly image processing choices can influence perceived structures. Nevertheless, even if the specific 5-point formation proves to be an artifact, Ray's original images have already achieved considerable value. They've compelled the professional astronomical community to re-examine 3IATLAS with heightened scrutiny, prompting a careful review of their own data. This re-examination seeks to identify structures that may have been inadvertently filtered out during initial analysis and to seriously consider the possibility that this interstellar visitor possesses a complexity exceeding the initial simpler observations. This imperative to look again constitutes the genuine legacy of amateur astronomy. It does not aim to supplant professional work, but rather to pose distinct, often unexpected questions. Amateurs approach the data with perspective unburdened by preconceived notions regarding what oughts or ought not to exist within the cosmos. Consequently, while their observations occasionally reveal artifacts, there are moments, rare but significant, when these untrained eyes perceive genuine truths before any other observer. Until NASA releases official images of 3IATLAS captured by the Hubble Space Telescope, the James Webb Space Telescope, or major ground-based professional observatories, Ray's footage stands as the most detailed view of the object currently accessible to the public. Astonishingly, it appears that, for the present moment, amateur observers are at the forefront of this unfolding scenario. The global community watches intently, waiting to determine whether these individuals have uncovered something truly extraordinary or merely exposed the human tendency to perceive patterns within darkness, even when deception is involved. Within hours of Ray's captivating images achieving widespread circulation, a wave of conspiracy-focused content emerged. These presentations featured intense musical scores, urgent voiceovers, and digital overlays drawing prominent circles around the 5 distinct points. Labels such as Escort Craft and Scout Probe adorned these markings. Assertions claimed NASA was actively suppressing evidence of intelligent surveillance. References were drawn to every notable unidentified flying object sighting documented over the preceding 5 decades. This followed a familiar pattern. A significant portion of the content presented was demonstrably unfounded. Lens flares captured in the original footage were mistaken for artificial structures. Halos appearing around bright stellar objects due to image sharpening techniques were interpreted as energy shields. Color variations resulting from sensor noise were reinterpreted as indicators of propulsion systems. For individuals lacking understanding of digital camera mechanics, data processing algorithms, or the propagation of optical artifacts during image enhancement, Ray's visual records could be construed to resemble almost any desired interpretation. However, here lies a crucial observation. If one removes the dramatic musical accompaniment and the entire conspiracy narrative framework, certain underlying observations made within these videos are not entirely without foundation. What becomes apparent is this: the 5-point configuration itself possesses an inherent strangeness, even though it does not constitute proof of extraterrestrial technology. The unexplained phenomenon centers around distinct luminous points appearing within the comet's coma, defying conventional astronomical interpretation. The precise geometric arrangement of these 5 points particularly perplexes optical physicists, not merely intriguing alternative theorists. While diffraction patterns naturally generate bright spots surrounding celestial bodies, These typically manifest as asymmetric spikes or isotropic blooms, never exhibiting the symmetrical ring formation observed. Similarly, dust jets emanating from a rotating nucleus can create multiple luminous regions within the coma. However, achieving perfect synchronization across 5 equidistant points demands either an improbable geometric alignment of surface vents or an unknown organizing principle dictating the pattern. Compounding the mystery is the observed flicker synchronization. Multiple independent observers analyzing processed ray frames consistently report that the 5 points do not fluctuate independently in brightness. Instead, they exhibit coordinated brightening and dimming, appearing to pulse in unison. This precise, non-random luminosity variance represents the kind of detail frequently exploited by speculative channels as potential evidence of artificial control. Yet, paradoxically, it also signifies a potential signature of an authentic physical process, even if that process remains entirely natural in origin. A plausible, though speculative, physical explanation involves rapidly rotating dust structures. If the comet's nucleus possesses a distinct shape, perhaps elongated or flattened, and undergoes rapid rotation, material ejected from its surface could form transient shells or rings. These temporary formations might persist for several minutes before dispersing. As the nucleus spins, these dust rings could intermittently intercept sunlight at regular intervals, creating the impression of synchronized flashing across the 5 fixed positions. This hypothesis, while requiring further investigation, remains grounded in established physics rather than science fiction, offering a potential naturalistic framework for the perplexing observations. Another scientific hypothesis proposes that electric fields within the comet's coma may generate the observed filamentary structures. As comets traverse the solar wind, they build up substantial electrical potential. This accumulated charge has the capacity to align dust particles into distinct configurations, drawing them into thread-like formations or gathering them at particular radial distances from the central nucleus. Laboratory simulations have conclusively demonstrated that charged dust grains naturally self-assemble into remarkably ordered formations under such conditions. If an object like Oumuamua exhibits intrinsic electrical activity, a plausible characteristic for interstellar bodies encountering the solar wind at extreme velocities, then these emergent electric fields could theoretically account for the geometric ray patterns visible in astronomical imagery. Some interpretations dismiss the electric field mechanism entirely, leaping directly to extraterrestrial explanations. Yet the core observation remains valid. The data genuinely presents a pattern exhibiting a degree of organization that warrants scientific inquiry. Where these alternative theories err is in the fundamental assumption that discernible structure necessarily implies intelligent design. Humans possess an innate cognitive tendency to identify patterns, a trait that manifests as perceiving familiar shapes in natural formations like clouds or detecting faces in geological features. This evolutionary adaptation, crucial for survival when interpreting potential threats in the environment, often leads to misinterpretations when applied to complex cosmic phenomena. The universe consistently generates symmetrical forms without any guiding intelligence. The precise hexagonal symmetry of snowflakes arises entirely from the molecular lattice structure of frozen water, not from conscious architectural design.
Saturn's magnificent rings display distinct layers and bands, not through deliberate design, but due to intricate gravitational dance performed by its moons. Similarly, the breathtaking spiral arms of galaxies emerge not from engineered artistry, but via fundamental forces of gravity and motion. Such cosmic symmetry remains profoundly captivating. Upon encountering it, particularly in unexpected realms, a primal human impulse arises, the question of its origin. This impulse intensifies dramatically when symmetry manifests within images of an interstellar traveler, an object hailing from beyond our solar system, potentially bearing relics or coded messages from distant civilizations. Consequently, certain online communities promoting extraterrestrial theories are mistaken in their core conclusions. Yet they are not entirely misguided regarding the strangeness itself. The reported 5-point configuration observed within its shape, provided this structure is genuine and not merely an artifact of image processing, signifies a form that defies conventional understandings of cometary structure. This anomaly demands investigation. It warrants serious consideration. The challenge lies precisely in taking such observations seriously requires meticulous, often tedious effort. Constructing complex simulations, rigorously testing alternative hypotheses, meticulously comparing the data against established cometary behavior, and patiently awaiting clearer observations. Conspiracy theorists, however, lack the patience for this rigorous empirical work. They seek immediate, dramatic answers. Scientists, conversely, operate comfortably within the boundaries of uncertainty. They understand that the vast majority of cosmic anomalies ultimately yield to straightforward terrestrial explanations. Having witnessed countless seemingly impossible observations dissolve under closer scrutiny, they approach such intriguing images with cautious skepticism, prioritizing the simplest, most probable explanation before entertaining more exotic possibilities. The caution against overinterpretation is entirely valid, yet it carries the risk of hasty dismissal. If these 5 distinct features are categorically labeled as mere artifacts without meticulous scrutiny, we could inadvertently overlook a significant breakthrough in understanding the behavior of interstellar bodies. Such premature judgment might cause us to ignore genuine physical phenomena that could illuminate previously unknown aspects of dust dispersion mechanics, rotational states, or structural formations within an active coma. As is often the case, the truth likely resides in a nuanced reality. These 5 points probably represent a composite of authentic celestial features and processing-induced distortions. Certain elements captured by Ray almost certainly correspond to real jets or localized dust concentrations present within the actual coma. But unlike normal comets, this comet appears to not produce the same level of dust as others. Such strange behavior demands investigation.
Simultaneously, other elements are almost certainly enhancement artifacts, bright spots artificially intensified through image stacking and sharpening techniques, rendering them more sharply defined than their true nature warrants. Disentangling these genuine features from processing illusions demands substantially improved observational data. This necessitates the release of professional-grade observations by NASA, coupled with independent analysis conducted by multiple scientific teams using calibrated instruments on 3 distinct data sets. Only then can we achieve definitive clarity regarding what constitutes reality versus visual deception. Nevertheless, this situation has produced one tangible benefit. The persistent focus applied by certain online commentators has ensured continued public attention remains fixed upon this anomaly. Consequently, when NASA eventually releases its comprehensive data, a substantial audience will be actively engaged and observing. Should any unusual patterns resembling rays-captured images emerge within the official datasets, the resulting public scrutiny will undoubtedly create significant pressure upon the scientific community to provide thorough explanations. Therefore, while the interpretations offered by conspiracy theorists are fundamentally incorrect, their core inquiry remains profoundly relevant. They are, in essence, posing the crucial question: what truly exists out there, and what underlying processes could account for its observed appearance? Even if the answer may seem mundane, posing the question remains essential. Occasionally, and with sufficient frequency to remind us of our limitations, the cosmos presents phenomena that defy conventional understanding. It is only through meticulous examination that we can discern whether 3IATLAS represents one of these extraordinary occurrences. This installment marks the 10th in a series dedicated to comparative analysis, focusing on Atlas, Oumuamua, and Boris. Over the span of 8 years, 3 celestial bodies have traversed into our solar system, each bearing origins distant from our own. These entities, shaped around another star, embarked on journeys spanning potentially millions of years across the vast expanse between stellar systems before being ensnared by the gravitational pull of our Sun, altering their paths within our cosmic neighborhood. Individually, each object exhibits peculiar characteristics, but when juxtaposed, a discernible pattern emerges. This pattern does not conclusively demonstrate anything, yet it prompts contemplation regarding our previous perceptions of interstellar space.
The moniker signifies scout or messenger in Hawaiian, marking it as the inaugural confirmed interstellar object detected traversing our system. Almost instantaneously, its strangeness became apparent. The orbital dynamics were anomalous. Oumuamua displayed a subtle acceleration as it receded from the Sun, exceeding what gravitational forces alone could account for. Though minor, this additional velocity was evident in the observational data, challenging established norms and leaving scientists intrigued. Comets gain speed through a process involving jets of vaporized ice erupting from their surfaces. These jets function like miniature rocket engines, propelling the celestial body forward. However, Oumuamua presented a stark contrast. It displayed no visible coma, no trailing tail, and no observable signs of such activity. Its diminutive size and remarkably rapid motion rendered detailed imaging impossible. Spectral analysis, though, revealed a dark reddish hue on its surface, characteristics far more akin to those of an asteroid than an active comet. This absence of expected activity raised the pivotal question: what force propelled Oumuamua forward? Numerous explanations emerged. One possibility involved outgassing of exotic volatiles, substances capable of vaporizing yet failing to generate a visible coma. Frozen nitrogen or hydrogen, for instance, could plausibly drive this acceleration, materials not commonly expected within our solar system, but potentially prevalent in the region from which Oumuamua originated. Another theory suggested its shape played a crucial role. Perhaps it possessed an elongated cigar-like form or was unusually flattened, resembling a pancake. Such a configuration could make it significantly more susceptible to being pushed by the gentle pressure exerted by sunlight itself. Intriguingly, one respected astronomer from Harvard University proposed an entirely different hypothesis. Oumuamua might be artificial. It could be the hull of a light sail or a probe, technology engineered by an advanced extraterrestrial civilization and adrift within the cosmic ocean.
It compelled astronomers to seriously entertain possibilities they would typically reject without hesitation. Then, in the latter part of 2019, Borisov appeared, representing almost the complete opposite of Oumuamua in nearly every observable aspect. The comet exhibits a distinct, prominent coma accompanied by a lengthy, elegant tail. Spectral analysis confirms the presence of well-known cometary compounds, namely carbon monoxide and water vapor, precisely the substances anticipated from an icy body warmed by solar radiation. Boris appears conventional and behaves predictably. Were it not established that it originated from an external star system, observers might readily classify it as merely another comet sourced from our own Oort cloud. Visible relief exists among astronomers. After all, such interstellar objects are fundamentally comets and asteroids merely traversing our cosmic neighborhood from elsewhere. However, Borisov possesses unique characteristics. Its carbon monoxide levels are exceptionally elevated, surpassing those typical of comets originating within our solar system. Furthermore, its dust emission fluctuates erratically, exhibiting unpredictable spikes and declines. Its central nucleus also displays signs of structural disintegration, shedding fragments as it approaches the Sun. This behavior indicates the comet is physically fragile, held together primarily by ice undergoing rapid sublimation. Despite these peculiarities, Boris remains comprehensible. Its actions fall within the spectrum of phenomena previously documented for solar system comets. It is undoubtedly exotic, yet not alien in the sense that provokes unease. Now, we encounter Atlas, which occupies an intermediate position between its two notable predecessors in the most unexpected manner. Like Oumuamua, Atlas manifests features incompatible with standard celestial models. These include a 5-point symmetrical structure, rapid rotational model or precessional wobble, and dynamic shifting formations within its coma that ray imaging techniques appear to capture. Contrasting sharply with Oumuamua's apparent inertness, Atlas demonstrates clear activity. It possesses a discernible coma and actively ejects dust and likely emits gaseous material as well. From an optical perspective, Atlas undeniably exhibits behavior characteristic of a comet, but much like its predecessor Borisov, Atlas appears to be fragmenting or undergoing significant structural changes. Telltale signs within the coma, the dark ridges, potential shadowing effects, and the observed shifting position of the bright core across sequential images strongly indicate processes are actively altering the nucleus itself. These changes may be reshaping the object or modifying its surface properties in real time. Crucially, either Oumuamua nor Borisov displayed symmetric features resembling Atlas's distinct 5-pointed pattern.
Furthermore, neither generated imagery that immediately suggested formation or escort phenomena. This unique 5-pointed structure is entirely new in the context of interstellar visitors. So, what implications does this hold? One interpretation posits that we are simply witnessing greater diversity as our observational sample size increases. Currently, only 3 interstellar objects have been identified, a number statistically insignificant. Had astronomers waited another 10 years and detected 30 such visitors, it's plausible each would possess its own distinct characteristics. The collective weirdness of dozens of objects might then average out to encompass a full spectrum of natural phenomena: elongated asteroids, fragmenting comets, or bodies exhibiting unusual rotational states. All such variations could be explained by the chaotic processes inherent in star system formation and material ejection. Alternatively, Atlas's unusual appearance might stem from a detection bias. Astronomers only register interstellar objects that exhibit striking features. Oumuamua was detected due to its rapid velocity and anomalous trajectory. Borisov was readily identified because of its prominent tail. Atlas's brightness and intense activity made it impossible to overlook. It's entirely possible that hundreds of unremarkable, dark and quiet interstellar rocks pass through our solar system annually, undetected and unnoticed. We are compiling a catalog of the unusual because those are the only ones we can observe.
However, there is a third possibility that is more challenging to ignore. Perhaps interstellar objects are more diverse than those within our solar system because they originate from a wider range of environments. Our solar system was born from a single molecular cloud surrounding a solitary star. Everything within it shares a common genesis, the same initial composition, formation, temperature, and pressure, and a shared bombardment history during the early tumultuous period. Interstellar objects, on the other hand, come from everywhere. Different stars, different nebulae, different episodes in galactic history. An object that formed around a hot blue giant would have a completely different thermal history compared to one that formed around a cool red dwarf. An object ejected from a system during a close stellar encounter might have a distinct structure from one that drifted away gradually over millions of years. If this is indeed the case, if interstellar space is filled with objects molded by wildly different processes, then we should anticipate every visitor to astonish us, not because they are artificial or anomalous, but because they are revealing what occurs in environments we have never sampled. 3IATLAS might have formed in a system with extreme tidal forces, resulting in internal structures or layering that produces symmetric outgassing patterns.
Alternatively, it could originate from a debris disk around a binary star, tumbling chaotically for eons until its rotation state locked into a complex precession. Or it could be a fragment from a larger body that shattered during a collision, with us now observing the geometric remnants of that breakage. All these explanations are natural in origin and do not require any involvement of intelligence or technology. Yet they each challenge the boundaries of our understanding of interstellar objects. The true significance of comparing ATLAS to its predecessors lies in this. We are not merely cataloging peculiar rocks. We are beginning to chart the diversity of planetary materials throughout the galaxy. Every interstellar visitor serves as a free sample from a star system we may never explore, a messenger bearing information from light years away. Asteroid Borisov taught us that some objects experience mysterious accelerations. Comet Borisov, on the other hand, revealed that some possess extreme compositions. An atlas, if the five-point formation hypothesis is confirmed, might teach us that some exhibit geometric structures previously unseen. Alternatively, it may simply teach us how easily amateur images of distant objects can be misinterpreted. We will not know until we examine further, until NASA directs its most advanced instruments toward 3IATLAS, unveiling what lies hidden behind the blur and noise of Ray's backyard telescope. Whatever is revealed will constitute one more data point, one more piece in the cosmic puzzle. 3 visitors have arrived, and if we continue to watch the sky, thousands more await. Such phenomena might illuminate why we perceive patterns in randomness, or simply demonstrate the universe's penchant for cosmic mischief. On the 6th of November 2025, NASA's Deep Space Network registered an unusual radio burst emanating from our Sun. It wasn't remarkable for its volume. Solar radio emissions occur constantly. Our Sun, a colossal sphere of plasma, undergoes ceaseless twisting and snapping within its magnetic fields. Each instance of a field line breaking and reconnecting propels particles outward, generating radio waves. Astronomers specializing in the Sun have meticulously categorized these emissions into distinct types, including Type 3 bursts and Type 2 bursts, based on their frequency and duration characteristics. However, this particular burst defied neat classification. It commenced as a classic Type 3 event, fast-drifting, high-frequency emission aligning perfectly with electron beams rushing outward through the solar corona. Yet, abruptly, the phenomenon paused. Instead of continuing its characteristic drift towards lower frequencies, the emission stabilized. Over the subsequent 17 minutes, it began pulsing. The rhythm wasn't random or chaotic. Instead, it hinted at regular intervals, a pattern that nearly resolved into consistent cadence.
The raw data displayed distinct peaks occurring approximately every 32 seconds. Then, the interval shifted to 41 seconds before fluctuating again near 30 seconds. Periodicity was present yet elusive, akin to grasping a rhythm that perpetually altered its tempo. This signal provoked division among heliophysicists. Some researchers contended it stemmed merely from multiple overlapping bursts. They argued that the complex interplay of coincidental timings, inherent in the sun's inherently messy activity, could easily create the illusion of a pattern. Dozens of intricate processes unfold simultaneously within our star. The argument went that if one observes the inherent solar noise persistently enough, one will inevitably perceive rhythms that lack genuine underlying structure. Careful analysis reveals that solar oscillations exhibit genuine periodicities lasting between 3 and 4 minutes. The sun vibrates much like a bell, resonating at distinct frequencies intrinsically linked to its internal architecture. These oscillations can modulate solar radio emissions, imprinting quasi-periodic patterns onto observational data. While not perfectly regular due to the sun's inherent turbulence, these patterns are consistent enough to emerge clearly through rigorous analysis. However, the primary point of contention lies in the timing. This significant radio burst occurred precisely during the period when 3IATLAS made its closest approach to the sun. Simultaneously, amateur astronomers globally directed their telescopes towards the comet, endeavoring to capture images that might reveal distinctive geometric formations. Furthermore, NASA was preparing to unveil its official observations of the event. Crucially, correlation does not imply causation. The sun remains indifferent to comets. Solar radio bursts exhibit no direct response to distant icy bodies situated millions of kilometers away. Therefore, the temporal alignment is most likely merely coincidental. Nevertheless, this connection becomes significant within the context of the 3IATLAS mystery. Solar radio emissions can indirectly disrupt observations by altering the space environment surrounding comets. This interference operates not by obstructing light or scrambling telescope mechanisms, but by influencing the plasma and magnetic fields in the comet's vicinity. The solar wind transports embedded magnetic fields and charged particles. When these magnetic fields fluctuate and particle densities surge, comets react physiologically. Their comas experience compression, dust tails shift position, and jets may activate or deactivate in direct response to changing pressure conditions. Consequently, if the solar radio burst coincided with unusual solar wind activity, then 3IATLAS's behavior might be a reaction to these specific space weather conditions rather than the comet itself.
The 5-point pattern observed could potentially be attributed to the comet's coma, responding to pressure waves within the solar wind. This phenomenon might involve dust gathering at particular distances, where the forces of incoming and outgoing flows reach equilibrium, as well as plasma formations at the boundaries of magnetic fields. This has indeed been noted in the past. In 2013, Comet Evenson demonstrated unusual coma structures as it neared the sun. Bright knots and filaments frequently emerged and vanished within hours. Further analysis revealed that these structures were linked to disturbances in the solar wind,
suggesting the comet was influenced by space weather, with its coma reflecting these effects. Could an identical process be occurring with Comet Atlas? Might the 5 points be artifacts of solar wind, transient structures that exist only because the sun is undergoing some unusual activity at present? While this scenario is plausible, it does not entirely account for the observed symmetry. Typically, interactions between solar wind and comets result in asymmetry, producing tails directed away from the sun and bow shocks on the sun-facing side. Achieving 5 evenly spaced bright points would necessitate either an exceptionally precise alignment of magnetic structures or a unique characteristic of the comet itself that facilitates a symmetrical response. Additionally, there is the issue of periodicity. If the solar radio burst pulses every 3 to 4 minutes, and the 5 points in ray images appear to flicker or shift on a similar timescale, is this a mere coincidence, or is there a physical connection? The sun's rotation at the equator takes approximately 27 days, further complicating the analysis of these phenomena.
They represent electromagnetic radiation traversing space, interacting with matter only when encountering a receiver precisely tuned to their frequency. This leads to a critical reconsideration. Perhaps the radio burst functions not as the initiating cause, but rather as a visible symptom, a direct signature of deeper disturbances within the solar wind. These disturbances simultaneously impact both the sun's corona and the comet. In this scenario, the observed periodicity offers a vital clue to the underlying physical process. Something inherent within the solar wind must be oscillating, generating pressure waves that propagate outward in ripples. Both the sun's radio emission and the comet's coma would then respond to this singular driving force emanating from the sun. Scientists are meticulously analyzing solar wind data collected by spacecraft such as the Parker Solar Probe and the Solar Orbiter, seeking potential correlations. Initial findings indicate heightened magnetic field variability during the specific period when Ray observed the phenomenon. While nothing extreme occurred, no significant solar flares or coronal mass ejections were detected, the data revealed increased turbulence and subtle, small-scale fluctuations. These variations, ordinarily unremarkable in isolation, might hold significance within the context of the 3-point alignment observed. They could potentially constitute the missing element explaining the precise timing of the 5 distinct points that appeared. This might, therefore, elucidate why Ray's observation occurred at the exact moment it did, even if he was unaware of the underlying cause. However, this solar activity could also be a red herring. The universe might have introduced random noise into the data stream at precisely the wrong moment, complicating the task of distinguishing genuine comet features from environmental effects. This inherent challenge defines the frustration of astronomical research. Unlike laboratory science, astronomers cannot control their experiment. They cannot deactivate the sun's magnetic field to observe the comet under different conditions. Instead, they must observe phenomena as they occur naturally and subsequently attempt to untangle the complex web of cause and effect after the fact. Yet this situation leads to a profoundly unsettling realization. If the sun can generate quasi-periodic radio bursts, exhibiting patterns that appear remarkably structured and regular, then the universe possesses the capacity to create deceptive patterns not merely in the images of remote comets, but potentially in any data considered objective. This includes trusted sources like frequency spectra, light curves, and time series measurements. We often place greater faith in the output of our instruments than in our own visual perception, a reliance that this possibility fundamentally challenges. Yet scientific instruments can similarly perceive illusory patterns when the genuine signal interacts with background noise in a specific manner. Distinguishing meaningful patterns from mere timing accidents demands far more than high-quality data. Accurate interpretation requires rich context, historical perspective, and comparison with previous occurrences. Currently, Comet ISON presents us with a pattern we cannot yet decipher. This occurs during a period when the Sun itself is also generating patterns we do not fully comprehend. Their connection remains uncertain. Perhaps they are linked, perhaps they are not. However, that possibility persists until understanding emerges. Are we observing a comet behaving in a genuinely unusual way, or are we witnessing a comet following its usual patterns while the Sun's activity introduces confusion into the background data? Furthermore, if the latter explanation proves correct, how many other cosmic phenomena, long considered mysteries, might simply result from unfavorable timing coincidences? Could they be intriguing objects observing during particularly noisy intervals, yielding data that appears significant but ultimately signifies nothing? This critical question occupies the minds of solar physicists during their late-night vigils at present, and discovering the answer holds significance far exceeding the case of Comet ISON. The 12th part discusses a breakthrough in quantum gravimetry. Gravity itself is imperceptible to direct observation. While we undoubtedly experience its effects, feeling it when we stumble or witnessing an apple fall from a tree, we cannot direct a telescope at an object and directly measure its gravitational field. Gravity does not emit light or photons. It manifests as the curvature of space-time, existing as something fundamentally invisible and silent. Until recently, this inherent invisibility rendered gravity exceptionally difficult to quantify. However, a significant advancement now allows us to measure it, albeit in an indirect manner. May 2025 marked a pivotal moment in geophysical instrumentation, as scientists from the National Institute of Standards and Technology unveiled a revolutionary advancement in quantum gravimetry. Their creation, a portable instrument comparable in size to conventional household refrigerators, achieved unprecedented sensitivity in detecting minute fluctuations within gravitational fields. This breakthrough enabled detection at sub-millimeter resolution, allowing researchers to identify gravitational anomalies caused by objects smaller than a typical grain of sand. While the foundational principles of atom interferometry had existed for decades, this implementation represented a significant leap forward in practical application.
The underlying mechanism relies on manipulating clouds of ultra-cold atoms through precisely calibrated laser pulses, creating two divergent paths through subtly different gravitational environments. When these atomic streams recombined, their interference patterns revealed minute variations in gravitational potential. Earlier versions of such technology required extended measurement periods, measured in hours, and operated exclusively within tightly controlled laboratory settings. The new system achieved comparable precision in field conditions within minutes, approaching fundamental theoretical limits of measurement accuracy. This capability holds profound implications for planetary science, particularly in characterizing small celestial bodies. Current methods for determining mass distribution of asteroids and comets necessitate spacecraft proximity measurements to observe trajectory deviations caused by gravitational influences. The unusual density profile of Comet 6-7P, serving as a prime example, exhibiting lighter than expected regions suggesting internal void structures, demonstrates the limitations of existing observational techniques. The Rosetta mission, requiring years of meticulous planning and a budget measured in billions, achieved what the proposed quantum gravimeter method might approximate. Picture instead directing such a device towards Saturn's diminutive moon Atlas, seeking to measure its gravitational signature from Earth. While mapping the entire object from such an immense distance would remain impossible, this sensitive instrumentation could potentially detect subtle gravitational anomalies. It could identify localized mass concentrations or denser regions exhibiting a stronger pull than their immediate surroundings. Crucially, if the hypothesized five-point formation orbiting the Moon's core is genuine, meaning distinct companion objects truly exist, a sufficiently sensitive gravimeter ought to reveal their presence. Each individual object would contribute its own unique gravitational signature, resulting in minute, shifting perturbations within the overall gravitational field as they moved in orbit. Recognizing this specific pattern would provide compelling evidence. However, a significant challenge presents itself. Atlas resides millions of kilometers away. Its estimated total mass, while sounding substantial at several billion tons, pales in comparison to Earth's nearly 6 sextillion tons. Consequently, the gravitational influence of Atlas at this vast distance is infinitesimally small. It would be completely overwhelmed by local gravitational noise originating from sources closer to the detector, the Moon itself, the Sun, or even mundane terrestrial phenomena like passing trucks on a nearby highway. Nevertheless, researchers are actively pursuing solutions. They are developing a next-generation quantum gravimeter slated for deployment in 2027.
Initially, this advanced device will operate aboard the International Space Station. Its eventual placement on a dedicated satellite, far from Earth's dominant gravitational interference, promises a dramatic leap in sensitivity, improvements measured in multiple orders of magnitude. This development holds particular significance when considering the study of interstellar objects. Deploying a quantum gravimeter in orbit during the next visitor's approach could reveal the object's hidden architecture without needing a physical probe. Such a device might detect internal fragments, record complex spin patterns, and identify concealed pockets of mass potentially responsible for unexplained movements. Specifically concerning the three-point formation designated as Atlas, the timing presents a significant frustration. The underlying technology is demonstrably feasible, yet it lacks deployment in a configuration capable of observing the object before it recedes beyond practical reach. By the time a space-based gravimeter becomes operational, Atlas would have been several years beyond its closest solar approach, rendered too dim and distant for detailed analysis. Without accelerated mission development, NASA maintains a rapid response program for unforeseen scientific opportunities, utilizing emergency funding upon discovery. 3IATLAS could potentially meet the criteria. Should the formation withstand rigorous academic review and subsequent data releases indicate truly anomalous characteristics, political support might emerge to expedite a gravimetric satellite launch. This satellite would require minimal complexity, a small platform carrying only one instrument. Achieving a 6-month development and launch timeline would demand intense effort, targeting the object to capture vital measurements. The goal would be to compare the observed gravity field with optical data for structural consistency. However, this entire scenario remains speculative at present. The quantum gravimetric breakthrough represents merely a powerful instrument awaiting a specific purpose. More profoundly, it underscores the existence of hidden cosmic structures. For centuries, our understanding of the universe has relied predominantly on electromagnetic radiation. Light manifests itself across a vast spectrum, encompassing everything from radio waves to gamma rays. This electromagnetic radiation has provided us with an unparalleled perspective on the cosmos. However, this view possesses inherent limitations.
Electromagnetic signals primarily reveal information about surfaces, regions of emission, or phenomena involving hot plasma and luminous dust. Crucially, it fails to disclose what lies hidden within celestial bodies. Internal architecture remains concealed unless that structure interacts differently with light compared to its immediate environment. Gravity, in stark contrast, operates independently of surfaces.
Its fundamental interaction responds to mass itself, regardless of location within an object. Consequently, a dense core buried deep within a comet's diffuse coma would remain undetectable to conventional telescopes, yet would be readily apparent to a gravimeter. Similarly, a hollow structure, such as a fragmented nucleus aggregated by loose rubble, would exhibit a gravitational signature entirely distinct from that of a solid boulder sharing the same dimensions. This profound difference is the reason planetary scientists view gravimetric technology with such intense interest. It offers the unprecedented capability to probe the interiors of asteroids, comets, moons, and any sufficiently massive object capable of generating a measurable gravitational field, revealing their true construction. Furthermore, if Comet Atlas indeed harbored some anomalous internal organization, perhaps influencing the distribution of its 5 observed points or causing its peculiar rotation, gravitational measurements would expose such hidden configurations. Gravity would not present visual imagery, but rather elucidate the very essence of mass, its precise location, distribution patterns, and dynamic movements. The potential discovery of 5 distinct gravitational sources orbiting Comet Atlas's nucleus, if detected by a quantum gravimeter, would undoubtedly fuel intense speculation and refuel existing theories. Proponents of artificial origins might seize upon such a finding as definitive proof of engineered structures or monitoring technology embedded within the comet. The reality might prove surprisingly ordinary. Imagine 5 distinct segments, dense cores of ice or rock, detached during an ancient close encounter with another star millions of years ago. These fragments have orbited their central mass ever since, tethered by their own faint gravity. Over eons, they've drifted slightly apart, yet remain sufficiently proximate to form a recognizable cluster within amateur astronomers' photographs. This scenario, while exotic and unprecedented for an interstellar traveler, would be entirely plausible within natural processes. Alternatively, the gravimeter could register a single, continuous gravitational field, devoid of substructure. This would definitively confirm the 5 apparent points as mere illusions, artifacts of dust concentrations, diffraction patterns, or subtle errors introduced during image processing. In either case, we would achieve clarity. We would possess an answer grounded not in interpreting ambiguous visuals or debating minute pixel details from amateur astrophotography, but in the precise measurement of gravity itself. This is the profound promise of quantum gravimetry. It does not supersede telescopes, rather it introduces an entirely new dimension to celestial observation. It allows us to perceive the universe not through the lens of light alone, but through the fundamental property of mass.
History consistently demonstrates that each time humanity develops a novel method to observe the cosmos, we encounter phenomena beyond our expectations. Radio astronomy unveiled pulsars and quasars. X-ray astronomy revealed the intense environments of black holes and neutron stars. Gravitational wave detectors are already capturing collisions and mergers previously unforeseen. So, what revelations await from quantum gravitometry? What hidden structures exist within objects we believed we comprehended? What unforeseen surprises lie within the mass distributions of comets, asteroids, and interstellar visitors? We stand on the precipice of a new era. The technology is within our grasp, and the devices are under construction.
In the coming decade, gravimetric mapping will become as commonplace as analyzing a spectrum. When scientists point these instruments at an interstellar object and generate their first gravitational map, we might uncover that the atlas of the solar system was only the beginning. Perhaps the peculiarities we observe are the norm in the cosmos. Each celestial body harbors mysteries within its internal structure, concealed from the eyes of light, but inscribed in the language of gravity. Alternatively, interstellar objects may reveal a mundane interior, with all the intrigue residing on the surface, the coma, the sublimation of ice, the flow of dust. Until we look, the truth remains elusive. Now, finally, we have a means to peer beyond the boundaries of visible light. In the 13th installment, we explore a discovery made by artificial intelligence. On August 20, 2002, a machine learning algorithm sifted through data from the Transiting Exoplanet Survey satellite and flagged something that shouldn't exist: a planet with an orbital eccentricity of 0.973. To put this into perspective, Earth's orbit is nearly circular, with an eccentricity of 0.017. Mercury, the most eccentric planet in our solar system, has an eccentricity of 0.206. Even Pluto, in the frozen depths, only reaches 0.25. An eccentricity of 0.973 signifies that the planet's orbit is barely closed, an elongated ellipse so stretched that at its farthest point from its star, it is nearly 90 times more distant than at its closest approach. The planet spends the vast majority of its existence far beyond the frosty limits of its solar system, only to plunge inward with terrifying speed for a fleeting, intensely hot passage near its star, before returning once more into profound darkness. Such an orbit should ensure the planet's destruction. Cataclysmic tidal forces during its close approach would likely tear it asunder. Subjected to cataclysmic thermal stress, shifting from near absolute zero in the outer cold to the searing heat of a star-grazing perihelion, the planet's crust should fracture, its atmosphere boil away, and its fundamental structure collapse. Yet the transit data is unequivocal. The planet persists.
It is approximately the size of Neptune and completes this seemingly impossible journey every 412 Earth days. Astronomers, naturally, began seeking explanations. The most straightforward involves a three-body interaction. Perhaps this planet shares its system with another massive world. Over millions of years, gravitational tugs during their close encounters could pump up the orbit's eccentricity. Eventually, one planet is hurled into this extreme, scorching path, while the other settles into a more stable, familiar orbit. Alternatively, a stellar companion, perhaps a brown dwarf or a distant yet undetected star, might perturb the planet's trajectory cyclically every few thousand years. This recurring nudge could prevent the orbit from gradually becoming circular, locking it into this perilous path. Another possibility is that this world survived a catastrophic event within its own system. Its parent star might have experienced a close encounter with another star, violently scrambling the orbits of all the planets present. Most planets would have been completely ejected, flung into the void of interstellar space. This Neptune-sized planet, however, clung desperately by the thinnest margin of orbital stability, left adrift in an orbit that is technically bound to its star, but only just. This artificial intelligence system sought not for impossible worlds, but for patterns inherent to known celestial bodies orbiting distant stars. Its training involved learning the characteristic signatures of planetary transits observed across thousands of confirmed exoplanets. Armed with this knowledge, the algorithm systematically scanned vast archives of astronomical data, identifying any instances matching those established patterns, and designated potential candidates for closer inspection by human scientists. Among these flagged entries appeared a specific object,
accompanied by a distinctive annotation. High-confidence detection, yet anomalous parameters demanding verification. Human astronomers subsequently examined the raw data themselves. They confirmed the transits were genuine phenomena and validated the orbital solution derived from the observations. Crucially, they verified the planet's extraordinary orbital eccentricity as 0.973, eliminating any possibility of a data processing glitch or instrumental misfit. Consequently, astronomers now documented the existence of a world whose properties defy conventional expectations. This discovery emerged from an algorithmic analysis that identified a subtle signal overlooked by human observers for years, despite the relevant data having been publicly accessible for some time. No one had specifically sought such an extreme case, leading to the oversight. This instance illustrates an emerging trend. Artificial intelligence systems are identifying anomalies within astronomical datasets at a pace significantly exceeding human capabilities.
This advantage stems not from superior intelligence, but from relentless perseverance. AI algorithms possess the capacity to meticulously compare every recorded object within extensive catalogs against countless theoretical models, consistently flagging outliers without fatigue or the inclination to dismiss unusual readings as mere errors. This tireless scrutiny reveals data points that challenge established norms. The connection to the enigmatic 3IATLAS phenomenon becomes apparent here. The distinctive 5-point structure observed within its rays represents a significant outlier. It does not conform to the standard models used to describe cometary appearances. Had an artificial intelligence system been trained on thousands of comet images and then tasked with classifying footage of 3IATLAS's rays, it would likely have identified the phenomenon as anomalous. However, the designation of anomalous inherently signifies deviation from the norm, not impossibility. This exoplanet definitively confirms its existence. Its characteristics are profoundly unusual. However, it undeniably orbits a genuine star, exhibiting a measurable real orbital period. The fact that such an orbit defied our predictions does not render it impossible. It simply indicates our current models were incomplete. The same principle may apply to 3IATLAS. Perhaps interstellar comets can display symmetric jet patterns not observed in comets within our own solar system. Perhaps objects originating from other stellar environments develop structures entirely unknown to us, formed under distinct physical conditions. The exoplanet's host star is an F-type star, notably hotter and brighter than the Sun. The planet itself might have originated farther from its star and migrated inward, influenced by interactions with a protoplanetary disk that was significantly more massive or extended than the one that gave rise to our own solar system. Alternatively, it could have begun life within a binary star system and entered this extreme orbit after its original parent star was stripped away. The precise mechanism remains unknown. Nevertheless, we accept its existence because the data provides undeniable proof. The observed transits are present. The calculated orbital parameters align perfectly with the measurements. Whether we understand how it arrived in this position or not, the planet is undeniably real. Should we therefore apply the same logical framework to 3IATLAS? Should we accept that the 5 observed points exist based solely on the data, even if a complete explanation remains elusive? This is the fundamental tension within scientific inquiry. Science mandates skepticism. It insists that extraordinary claims require extraordinary evidence. An anomalous exoplanet detected through space telescope photometry represents a distinct category of discovery compared to an anomalous pattern captured in amateur astrophotography.
The fidelity of observational data varies significantly. So too does the potential for spurious signals to arise. Yet crucially, both datasets represent genuine phenomena unfolding within the cosmos. Each
pushes the boundaries of our comprehension, consistently reminding us that the universe exceeds the scope of our current models and surpasses our wildest conceptions. The discovery of the exoplanet further underscores a vital principle regarding rare occurrences or edge cases. Statistically, the vast majority of astronomical objects conform to established norms. Planets typically exhibit moderate orbital eccentricities. Cometary nuclei generally develop disordered, asymmetric halos. The familiar bell-shaped distribution possesses a robust central peak, yet its extended tails reach depths far beyond common expectations. Evidence includes planets with orbital eccentricities approaching an extreme value of 0.97. There may even exist comets displaying remarkably symmetrical five-fold jet patterns. These cases are exceptionally uncommon, yet their rarity does not imply absolute non-existence. Should an observer catalog 1,000 comets and 999 display typical chaotic structures, scientific models would naturally be constructed around those prevalent examples. Consequently, upon encountering the 1,000th comet exhibiting an unusual feature, the initial skepticism would likely attribute it to instrumental error or observational artifact. However, the 1,000th comet can indeed be authentic. Sometimes, the anomaly itself becomes the most potent teacher, conveying insights inaccessible through the study of typical cases alone. This fundamental recognition defines the essence of edge case cosmology. The rare objects, the persistent anomalies, the entities bordering the permissible limits of physical law. These are the very phenomena compelling us to transcend existing frameworks. They delineate the true boundaries of possibility and chart the unexplored territories of phase space that ordinary objects never traverse. The 3IATLAS comet presents two distinct possibilities. It could represent a rare interstellar visitor whose unusual characteristics stem from formation processes alien to our own solar system, exhibiting structures or behaviors seen in only 1 in 1,000 similar objects. Alternatively, it might simply be a conventional comet whose appearance has been artificially enhanced through amateur image processing techniques, making it seem more extraordinary than its true nature warrants. Regardless of its origin, the recent discovery of a distant planet with an orbital eccentricity of 0.97 serves as a powerful reminder. Nature consistently produces phenomena beyond our expectations. Each time human understanding declares something impossible, reality finds a way to challenge those boundaries.
Therefore, when NASA releases its official 3IATLAS data, displaying what professional-grade imagery reveals, we must approach the findings with an open mind. There remains a genuine possibility of encountering something genuinely unconventional, not necessarily of extraterrestrial design, but sufficiently strange to demand novel scientific explanations. The precedent set by the planet with its remarkably high orbital eccentricity is instructive. Found hidden within publicly available data by artificial intelligence, it demonstrated that significant anomalies can exist undetected despite widespread access. This suggests the comet's 5 bright points ranged in a ring might be genuine. Perhaps this configuration occurs when specific formation conditions combine with a particular spin state during ejection into interstellar space. Or conversely, the phenomenon could be purely an artifact of observation or human interpretation. Only when examined with instruments surpassing the capabilities of amateur backyard telescopes will the truth emerge. This experience with the seemingly impossible exoplanet underscores a crucial scientific principle: observe with meticulous care,
Rely on the data itself rather than assumptions. Crucially, do not automatically dismiss anomalies as mere errors. Sometimes technological milestones emerge not as sudden breakthroughs, but as gradual discoveries. In September 2025, the National Ignition Facility in California reported a major achievement. They had sustained a net positive fusion reaction for 32 seconds. This marked a significant departure from earlier experiments, which produced only fleeting microsecond pulses, or results that barely achieved energy balance under idealized and challenging circumstances. 32 full seconds of uninterrupted fusion, yielding more energy than was consumed in the process, represented a leap forward that had been pursued for decades. During those 32 seconds, the plasma reached temperatures of 150 million degrees Celsius, a value 10 times greater than the core temperature of the Sun itself. Within a magnetic confinement system, barely larger than a beach ball, hydrogen nuclei moved so rapidly that their collisions were violent enough to overcome the natural electrostatic repulsion between positively charged particles. They fused into helium, releasing vast quantities of energy in the process. Maintaining such plasma stability for even a single second had previously been considered an engineering challenge bordering on impossibility. The magnetic fields required to contain it had to be shaped with extraordinary precision. Any minor fluctuation or instability would cause the plasma to make contact with the chamber walls, instantly extinguishing the reaction.
The process resembled balancing a fiery spinning top upon the tip of a needle, a task made all the more daunting by the fact that the spinning top itself was composed of material akin to the interior of the Sun. Remarkably, for 32 seconds, the system held. The plasma remained confined, fusion reactions continued to occur without interruption, and when the experiment was deliberately terminated, not due to equipment failure but by human decision, the data revealed something surprising. The plasma had organized itself into unique filamentary structures, with luminous regions rotating around the central axis in patterns that appeared almost geometric. Although not exhibiting perfect regularity, plasma turbulence displays a degree of underlying order surpassing that of completely random chaos. This phenomenon holds no surprises for specialists in plasma physics. Hot plasmas, by their nature, frequently manifest behavior that defies intuition. They spontaneously generate coherent structures, magnetic islands, and helical filaments. This occurs because charged particles trace the paths of magnetic field lines, and these field lines mutually influence one another. What may appear as pure chaos over brief intervals often reveals surprisingly ordered patterns when observed over extended durations and across broader scales, tracking the evolution of these structures. Here's where this plasma behavior becomes particularly relevant to the enigmatic 3IATLAS formation. The 5-point structure currently under debate appears strikingly organized. Critics argue that this level of geometric precision seems almost unnatural for a chaotic system. However, consider this: fusion plasma resides within the most turbulent and chaotic environment humanity has managed to create. Yet within this extreme turbulence, it consistently develops spontaneous geometric patterns. If such organization can arise in the intensely chaotic setting of a fusion reactor, perhaps a similar process could occur within the plasma streaming from a comet. Comet nuclei are inherently composed of plasma, ionized gases, and charged dust particles. This material interacts dynamically with the Sun's magnetic field while simultaneously being buffeted by the solar wind. While the underlying physics differs significantly from laboratory fusion reactions, certain fundamental principles remain identical. Crucially, temperatures are orders of magnitude lower, and particle densities are vastly more sparse in the cometary environment. Nevertheless,
the core mechanism persists. Charged particles moving within magnetic fields possess a remarkable capacity for spontaneous self-organization.
These ripples gradually evolve into pronounced waves and eventually give rise to distinct swirling vortices. When these vortices emit light, they can manifest visually as bright, knot-like features within the plasma stream. Should the atmosphere surrounding a comet's nucleus, known as the coma, release streams of gas and dust from numerous vents, and these streams come into contact with the solar wind, a fascinating phenomenon can occur. At the point where these two distinct flows meet, Kelvin-Helmholtz vortices may begin to form. Astronomers have previously captured images of similar vortex structures within the magnetotails of planets using space-based observatories. These formations consist of luminous knots of plasma arranged with remarkable regularity, a pattern entirely governed by the principles of fluid dynamics. Could such vortices potentially account for the 5 distinct points observed on the comet? It remains a plausible possibility. However, realizing this explanation would necessitate a very specific set of conditions. The solar wind must possess precisely the right characteristics. The comet's outgassing rate needs to fall within a narrow optimal range, and the observer's viewpoint must precisely align to show these structures edge on. While this scenario involves considerable specificity, it is grounded firmly in established physics, not mere conjecture. This connection to physical law underscores a profound aspect of nature's behavior, the recurring theme of symmetry. Consider the recent advancements in fusion research. Engineers meticulously designed reactors aiming for a perfectly smooth and symmetric containment field for the superheated plasma. Yet, the plasma itself dictated the emergence of bright, filamentary structures. These intricate patterns did not result from deliberate engineering, but arose spontaneously from the fundamental equations dictating the movement of charged particles under extreme conditions. Nature consistently manifests such self-organizing principles across vastly different scales. Just as wind sculpts sand dunes into repeating wave-like formations across deserts, or atmospheric currents create aligned rows of clouds known as cloud streets, spiral galaxies develop their striking arms. These galactic structures, though appearing meticulously arranged, are ultimately the consequence of density waves propagating through rotating disks of stars and gas. Humans by nature tend to interpret these regular patterns as evidence of design or intention. We instinctively imagine forces arranging the sand grains, orchestrating the clouds, or constructing the galaxy. Yet these complex forms are entirely spontaneous. They arise inevitably from simple physical rules operating unrelentingly until structure emerges triumphantly from apparent chaos. The central question concerns the nature of the 5 distinct points identified within the 3IATLAS phenomena.
Do these formations represent emergent structures within plasma or dust aggregating into symmetrical patterns dictated by underlying physical laws? Alternatively, are they merely artifacts, processing glitches amplified by stacking algorithms into patterns that appear significant? Crucially, fusion data alone cannot provide a definitive answer. However, it does demonstrate a fundamental principle. Exotic environments readily give rise to complex, exotic structures. This observation serves as a vital reminder that possessing excessive organization is not, in itself, evidence of artificiality. Nature consistently produces intricate order, often exceeding what human engineering can achieve. Consider the Sun's corona as a prime example. This region is threaded with magnificent arching loops of superheated plasma connecting active regions on the solar surface. These luminous structures remarkably resemble meticulously arranged suspension cables spanning a bridge. They exhibit precise geometry,
smooth flowing curves, and endpoints that precisely align with corresponding features observed in the photosphere below. Yet no architect designed these loops. Their formation is a direct consequence of fundamental physics. Magnetic field lines inherently seek to minimize their energy, finding the most efficient, shortest path between regions of opposite polarity. The resulting structure emerges inevitably from physical necessity, not deliberate design. Imagine encountering the sun for the very first time, unaware of its true nature. Observing these intricate coronal loops through a telescope, someone might reasonably conclude they appeared artificial, far too organized to be natural. They would likely insist that no known natural process could generate such perfectly defined geometry. That conclusion, however, would be demonstrably incorrect. Yet the error would be entirely understandable, born from our innate pattern recognition instincts. This is the precise cognitive trap we find ourselves confronting regarding the 3IATLAS case. Our minds instinctively engage in pattern matching, compelled to judge whether the 5 points manifest an organization so extreme that it defies natural occurrence. The complete natural appearance of interstellar comets remains unknown to us. Only 3 such objects have ever been observed within our solar system. This limited sample size makes it impossible to determine what constitutes typical cometary behavior. The striking 5-fold symmetry observed in Comet 3I/Atlas could represent a rare but natural phenomenon. Perhaps this unique structure arises under very specific conditions, comets possessing particular rotational speeds, exhibiting distinct jet configurations, and interacting with the solar wind at precise distances. It is equally plausible that if an upcoming interstellar visitor displays similar symmetry, it will simply become another documented example within the established study of comet dynamics.
Conversely, this configuration might be entirely unique to 3I/ATLAS itself, a singular alignment of circumstances producing a phenomenon we may never encounter again. Drawing an intriguing parallel, a fusion reactor experiment achieved plasma confinement for 32 seconds. This brief duration revealed that plasma can maintain its structure significantly longer than previously anticipated. The experiment unveiled unexpected internal formations and critically demonstrated that complex, high-energy systems often defy predictions derived from simplified theoretical models. Comet 3I/ATLAS itself embodies such a complex, high-energy system, traversing the void while absorbing solar heat and engaging with magnetic fields and particle streams. Its enigmatic structure might stem from the incompleteness of our current predictive models. Alternatively, we might be overinterpreting the observations altogether. The 5 distinct points could merely be optical artifacts, lens flare or sensor anomalies, hot pixels. Within weeks, such features might fade from public memory once NASA's more conventional data portrays 3I/ATLAS as a routine, unremarkable comet. Yet the 32 seconds of sustained fusion power provide compelling reason to maintain intellectual openness. Extreme cosmic environments often yield extraordinary phenomena, and occasionally, just occasionally, these peculiar results represent genuine discoveries. Part 15. The Dark Ring Nebula Mystery. January 2025. An amateur astronomer in Australia shares a newly processed photograph of a planetary nebula, a celestial object known to astronomers for many decades. The nebula itself presents no unusual characteristics. It consists of a dying star, its intense ultraviolet radiation stripping electrons from surrounding shells of gas it expelled long ago, causing the material to glow softly. However, the specific image processing technique employed revealed intricate details previously unnoticed. Dark, concentric rings appeared as faint, shadowy bands within the nebula's structure, exhibiting a remarkable circularity and precise, even spacing reminiscent of ripples frozen in time. Within hours, the image spreads rapidly across online platforms. Speculation explodes. Many claim this discovery constitutes evidence of artificial megastructures. They propose the rings are Dyson rings, vast human-made shells constructed around the dying star to capture its dwindling energy output. The rings' unnerving perfection seem to defy nature, they argue, asserting that natural phenomena rarely, if ever, produce such perfectly spaced concentric circles. Yet nature consistently demonstrates such patterns. Within the following week, professional astronomers release their detailed analysis. The dark rings are conclusively identified as interference shadows.
The nebula's intricate structure stems from multiple shells of ejected material, each deposited during distinct phases of the star's final evolutionary stages. Each successive shell possesses a slightly greater density than the gas surrounding it. As light radiating from the central star traverses these denser concentric shells, it undergoes diffraction and scattering. This interaction creates shadow patterns within the less dense material located behind the shells. The apparent perfect circles result purely from geometry. The nebula happens to be positioned almost directly face-on relative to our planet. We are observing straight down the axis of a structure that is inherently symmetrical, causing the spherical shells to project as perfect rings onto our sky. A different viewing angle, such as from the side, would reveal these structures as elongated lobes and irregular filamentary forms. No mystery remains. The phenomenon is fully explained by well-understood natural processes. The remarkable uniformity of the spacing originates from fundamental stellar physics. As stars approach the end of their life cycles, they often exhibit periodic pulsations. With each pulsation, a distinct shell of expelled gas forms in space. The precise interval between these stellar pulses is governed by the star's specific mass and chemical composition. In this particular case, the timing of the pulsations resulted in shells distributed across space at approximately equal intervals from one another. This intricate pattern arises entirely from natural stellar processes. No intelligence, no deliberate engineering involved, merely a dying star behaving according to its inherent physical nature. Our viewpoint, however, happened to offer an angle that made the structure appear deceptively orderly. Prior to this scientific explanation gaining acceptance, the Dark Ring Nebula became the subject of intense speculation. It was hailed by some as definitive proof that highly advanced civilizations construct vast shells around stars, suggesting tangible evidence of extraterrestrial life. Yet lies an uncomfortable reality. Those drawn to this conclusion were not acting irrationally. They were examining data that genuinely presented a structured, symmetrical appearance and reasonably asked the fundamental question: what entity or process could create such a distinct pattern? Their critical error was halting their inquiry prematurely. Having perceived the pattern, they concluded its artificial origin without sufficiently investigating whether known natural phenomena could adequately explain it. Crucially, the instinct to identify the pattern itself was not flawed. That innate ability for pattern recognition functions precisely as it evolved to do, to discern order within complexity. The enduring lesson drawn from the Dark Ring Nebula experience is that symmetry alone serves as a profoundly unreliable indicator.
The universe constantly generates symmetric forms: spherical stars, circular planetary orbits, hexagonal ice crystals, spiral galaxies. None of these intricate shapes demand intelligence for their formation.
They simply represent the geometries most readily favored and produced by the fundamental laws of physics. Human cognition naturally seeks patterns of purpose and design. We instinctively attribute symmetry to intelligent action, a survival mechanism honed for terrestrial environments. Spotting perfectly aligned objects, we presume an architect. Seeing flawless circles, we imagine an artisan. This evolutionary shortcut serves us well among familiar surroundings. However, applying this same intuition to the vast cosmos proves misleading. Space teems with spirals, rings, and radial symmetry, yet virtually all such formations arise from fundamental physical forces. Gravity sculpting galaxies, rotational dynamics shaping nebulae, pressure gradients concentrating cosmic dust, and immense timescales enabling natural processes. The question then arises regarding Comet Atlas. If multiple professional observations confirmed the existence of distinct luminous points forming a precise ring encircling its core, we must consciously suppress the immediate impulse to declare artificiality. The Dark Ring Nebula presented a similar deceptive symmetry before astrophysical analysis revealed its natural origins. Numerous plausible natural mechanisms could explain symmetric patterns in cometary phenomena. Narrow jets emanating from a rotating nucleus can align into rings. Plasma structures can self-organize along magnetic field lines. Concentrations of dust can stabilize at specific orbital distances governed by pressure equilibrium. None of these processes are exceptionally common. Yet, uncommon occurrence does not equate to impossibility. What remains essential is acquiring superior observational data. We require unprocessed, raw measurements captured by precisely calibrated instruments. We need spectroscopic analysis revealing the composition of the anomalous bright points. We need time-resolved photometry documenting their precise movements. We need multi-wavelength imaging to determine if these points emit distinctively in infrared or ultraviolet bands compared to the surrounding coma material. The forthcoming NASA data release promises significant insights. The Hubble Space Telescope has already scrutinized the comet structure, with the James Webb Space Telescope likely having targeted it as well. Furthermore, ground-based observatories employing intelligent mirror systems capable of counteracting atmospheric distortion have almost certainly captured images surpassing the quality of Ray's amateur recordings. When this professional data becomes publicly available, three distinct outcomes are possible. The first outcome envisions the geometric pattern vanishing entirely.
Professional observations will reveal a typical comet exhibiting an asymmetric and turbulent coma. No discernible geometric patterns or bright rings will be present. Ray's formation will then be conclusively identified as an artifact, amplified by electronic noise, and misinterpreted through the lens of internet speculation seeking intrigue. In this scenario, public interest wanes, conspiracy theories dissipate, and the Three-Eyed Atlas will be remembered solely as another interstellar traveler, noteworthy for scientific study but lacking dramatic significance. The second outcome suggests the 5 points remain, yet a plausible natural explanation emerges. Rigorous scientific analysis will attribute them to identifiable features such as powerful jets, concentrated plasma knots, or dense dust aggregates. While the symmetric arrangement may prove exceptionally rare, it will be demonstrably explainable through known physical processes. This scenario will fuel scholarly publication, refine existing models, and eventually see textbooks acknowledge symmetric comet structures as a footnote, resolving the mystery through understanding rather than disappearance. The most intriguing possibility sees the 5 points persisting, defying all conventional explanation. Professional imaging will confirm the precise pattern, while spectral analysis will reveal the points possess anomalous chemical compositions or emission characteristics.
Time-lapse sequences will document movements inconsistent with established comet models. This unresolved enigma will likely divide the scientific community. Some researchers will contend we are overlooking fundamental aspects of comet physics, while others will insist the observations represent something entirely unprecedented in our solar system. The pattern endures, the mystery deepens. The revelation that would fundamentally alter our understanding lies not in confirming artificiality, but in proving our current models are incomplete. Such a discovery would ignite entirely new research avenues, inspire fresh exploration missions, and compel us to fundamentally reassess the potential nature of interstellar objects traversing our solar system. Yet the critical question remains unresolved. No one possesses definitive knowledge about the true explanation. Every individual holds an opinion, convinced whether the observed images depict genuine phenomena or mere artifacts. However, personal convictions carry no weight. Only empirical evidence holds sway. Remember the Dark Ring Nebula, deemed impossible until meticulous calculations revealed its diffraction patterns. Recall the peculiar appearance of 3IATLAS until subjected to rigorous analysis. Thus, we await. NASA is meticulously reviewing their collected data. Scientists fervently debate within conference rooms and digital correspondence. Peer reviewers scrutinize complex calculations.
Somewhere, an investigator is undoubtedly unraveling the actual nature of the object. Its existence is certain. The possibilities, however, remain uncertain. It could signify nothing at all or something profoundly significant. The comet itself remains utterly unconcerned with our conjectures. It continues its indifferent rotation through the inner solar system, executing its natural functions without regard for the telescopes trained upon it or the heated discussions unfolding on Earth. When the definitive data emerges, when we witness what professional instruments have truly recorded, we will discern whether Ray encountered a genuine discovery or merely illuminated the remarkable ease with which human perception can be deceived by patterns within darkness. Regardless of the outcome, the saga of 3IATLAS serves as a vital reminder. The cosmos manifests strangeness not through the presence of aliens or manufactured structures, but purely through the intricate workings of physics. Our understanding remains incomplete. Each observation presents an opportunity to uncover something previously unknown. Every anomaly represents a potential gateway toward deeper comprehension. Or perhaps it signifies mere background interference, the human tendency to perceive patterns within randomness, a fundamental aspect of our cognitive nature. However, definitive knowledge eludes us until we engage in deliberate scrutiny, utilizing the most advanced instruments available and applying the sharpest analytical focus we can muster. This rigorous approach constitutes our sole path forward. We must proceed not through conjecture or unfounded theories, nor through reliance on unverified imagery and online discourse, but through meticulous observation, meticulous analysis, and the persistent dedication inherent in scientific endeavor. Eventually, we will unravel the nature of 3IATLAS. When this occurs, the revelation will either validate our existing assumptions or impart knowledge entirely unforeseen. This duality, confirmation or unexpected insight, embodies both the promise and challenge posed by every cosmic enigma. One can never predict which outcome awaits until the empirical evidence is obtained. And frequently, universe offers surprises that defy expectation.